So Alex, will you be able to show the slide for Invest Hong Kong? Invest Hong Kong is our event sponsor today. They have a special program. Alex, if you can show the next slide. They are going to have a Start Me Up Hong Kong Festival coming up next month in San Francisco. So please look them up and see this is maybe the right event for you and your team to join. So with that, so this, Jason, can you help with the audio? There's some background noise. You know, let's take care of that before we move on to the first speaker. Thank you, Jason. Okay, so let's start with our presentation portion of today's program. Again, my name is William Koo. I'm going to introduce our speakers this afternoon. Our first speaker today is Ted Spears. Ted Spears is a technical fellow at Microchip's FPGA business unit, where he is responsible for defining its roadmap for low power, secure, and reliable FPGAs, as well as SoC FPGAs. Ted is a RISC-V leader and evangelist, and has served on the board of directors of RISC-V International since its inception in 2016. He joined Octal, which is now part of Microchip, in 1987, and held roles in process engineering and product engineering before assuming his current role in 2003. He is a co-inventor on 35 US patents. Prior to joining Octal, he worked at LSI Logic. Ted has a Bachelor of Science in Chemical Engineering from Cornell University. The title of his presentation today is RISC-V and the Future of Computing. So, ladies and gentlemen, please help me to welcome Ted Spears.
Thank you for that introduction. Let me see. So I'm going to start sharing. I think that's how it's supposed to work. Share screen. Share that screen. And then start from the beginning. People see that?
Not yet.
Not yet.
Oh, great. Got the latency here. So that wasn't showing. Let's see here again. Share screen, screen one. Okay, maybe that's my problem there.
Okay, we saw it.
We can see something.
Yeah, so how about that?
We see your email, not the slide. So the slide in the front. It seems the email is in front.
So why is it sharing that screen? So we should have, sorry about this. Share screen. Okay, one more time. I can do this. Okay, that screen to, sorry about that.
Yes.
Is that better? All right, sorry about that. You know, I don't know how many times I've tried that. All right. Okay. Yeah. Yeah. Thank you very much for the introduction. Yeah. My name is Ted Spears. and my talk is RISC-V, the future of computing. I definitely appreciate the opportunity today that CASPA is giving me to speak, and hopefully after today, you'll want to have me back. All right, so about me, I think that's all you need to know. I got my WeChat QR code, social media, I'm at Ted Spears. And I think we've gone over this. I did graduate from Cornell University. What's a little bit unique about me probably in this audience is my bachelor's degree is actually in chemical engineering. Technical fellow at Microchip FPGA business unit, and the member of the RISC-V International's board of directors since its inception. So definitely proud of my role there. I've been an active promoter of RISC-V, spoken at 16 events. This is, I guess, number 17. And, hundreds of people around the world heard of RISC-V for the first time from me, I'm pretty sure. I also drove the creation of the Security Standing Committee. One of the attractions to RISC-V in our organization initially was the opportunity to kind of get security right with RISC-V. And so security is a first-class citizen in RISC-V International. And, most recently I recruited our CTO, Mark Himmelstein, who I'd recommend you guys invite, but the organization has made huge progress as far as its productivity, thanks to Mark's leadership, and you'll see some of that today. So the content today, I will indulge myself and talk a little bit about the Microchip FPGA business unit. I'm actually representing myself today, but Microchip FPGA business unit is a big part of myself. Share some RISC-V International news, and then talk about the RISC-V Vector ISA, give you a brief introduction into that, and some examples, and then start talking about an emerging pattern in compute, give you some examples there, and then pull it all together, which I'm going to call a framework for the golden age of computing, and then finally some calls to action. So our FPGAs, we have a flagship family is called PolarFire, and it comes in two varieties, an FPGA and then also an SoC FPGA. So that means a microprocessor is embedded with the FPGA. And we're distinct because it's a RISC-V microprocessor, quad-core application processor based on the Sci-5 chip. So we're one of the first RISC-V chips out there that you can actually program with. There's 2 billion RISC-V devices have shipped, but most of them are deeply embedded, so the user is not programming them. So to support PolarFire SoC, we've built an ecosystem to a RISC-V based ecosystem to support PolarFire SoC. So that's all the ecosystem type stuff, tools, boards, OSs. It's all part of the ecosystem, and it's pretty sizable at this point with some pretty famous companies involved, including example Green Hills Software, mission critical for a lot of industries. So we have a board, the first board out, it's called the Icicle Kit. So you see there in the middle, the Microchip RISC-V shiny PolarFire SoC device. So this is a basic development board. But our partners make boards as well. So you can get boards from these 6 companies shown here for different form factors and domains. And then we also introduced what we call the Smart Embedded Vision Kit. So this PolarFire SoC, you can hook it up to cameras and displays, run your vision stack on the RISC-V, and then do any kind of vision acceleration using the FPGA fabric. So I've been sharing this. This is how we view the compute, and been sharing this for a while. It's not that unique at this point, but on the left there, you see devices and sensors, and actuators. I kind of view those as the nerve endings of a being of some kind. The cloud represents the brain, and in between, you've got kind of the nerve centers or the nerves transporting the sensors all the way up to the cloud. So megatrends here, we've of course you got exponential growth in IoT of the sensors, and there's increasing human-machine interaction there. In the brain, cloud, massive data is being processed increasingly, but there's a problem where there's a latency between the sensor and the cloud. So more and more compute is being moved into the edge, so-called edge. so you can handle all these sensors more locally. So power used to be, not customer would say they were interested in power, but they wouldn't really make buying decisions. But now power is almost the primary factor. Whether if you're at the edge or the sensors, you care about supply or battery life. If you're in the cloud, you basically care about your electricity bill. You're paying $6 per watt per year in this massive facility. It's best to last 20 years, and you want to improve its productivity all the time. And then in the edge, it's almost about moving heat. This is where you see fanless, on-premise or outdoor enclosures. So it's heat removal. It's the power problem in the middle. Solution trends. We already talked about pushing compute loads from the cloud, from to the edge into the devices. Heterogeneous compute paradigms and accelerators solve some of the power problems today. Hardware and security solutions for the device. So it used to be, if all the compute's done in the data center, it's behind guards and gates and guns. But now your compute is being deployed out physically where it's reachable. So you have to have hardware security. And then safety and reliability is increasing because of the human machine interactions. So, where our FPGAs fit in is kind of in here, really at the edge. We're not the microwatt FPGA, and we're not the data center FPGA, but we really fit in here where you want to accelerate without heat problems, securely and reliably. So we are very differentiated in these areas. So we operate in the harshest environments. And if you want to talk harsh, and we're talking Pluto, Jupiter, Saturn, Mars, those are pretty harsh. And also any airplane you fly today has hundreds, if not thousands of our FPGAs on that. We have unique features that make us reliable. Womb to tomb security, and basically when our chip comes out of the fab, first thing it sees in life is an HSM, and we're injecting keys into our devices through the whole manufacturing process, and then we can carry it on so the customer can then layer his security on top of the secure HSM secure base that we've already established. So with this, you can secure your supply chain, and then you can also secure your data in your application. Then finally, low power. This is a competitor FPGA. This is in the lab running an application with an infrared camera, and you see that max is about 75 degrees centigrade with the competitor FPGA. So same environment, but polar fire FPGA, basically full 20 degrees lower. So you imagine what that has to do in a real environment where the ambient is not 25 degrees. So our low power, we like to joke, our goal is to put fan companies out of business. So hopefully not putting any of you, our listeners, out of business here. But also we make the impossible possible. We can make people build equipment and form factors they couldn't do without our FPGA. So they're not lining up to give testimonials because in many ways, polar fire is the secret sauce in their equipment. So moving on to RISC-V, big year last year, like I mentioned, over 2 million devices, but this was recent news. Intel joins RISC-V International. The headline is a little bit fake news. They definitely created a $1 billion innovation fund. RISC-V is a key part of their innovation fund. So if you have a RISC-V solution, RISC-V IP, they're willing to invest in you. I do want to mention that Intel is also proud of the fact you can get, they actually support ARM as well. But I showed their innovation partners that are all part of the RISC-V International there on the right. So then, speaking to our CTO's ability, we ratified 15 new specifications at the last summit. So that was great progress. Excuse me. Click 1, 2 quickly. All right, so the vectors is what I'm going to talk about, and then illustrate some examples with Andy's in Sci-5 in the talk here. So let's look at the vector ISA. So RISC-V is an open standard, so everything, all the specs are available on GitHub. But the core of the vector ISA is the 32 vector registers of a certain length. It's a variable length. It's up to the implementer, but the maximum they could choose is 2 to the 16 or 64K bits. So you got these 32 vector registers on your chip, and then we have what's called the state registers, configuration state registers, and one of them is read-only. It's VLEN-B. So when you have to decide how big your vector engine is going to be, or how big, and that's basically the length of that vector. So that's encoded in hard, and so the software needs to read that to actually figure out how to run. But we'll use this example of VLEN-B at 32 bytes or 256 bits. So another vector is, or register is V-type. So this one is writable. So your code is actually while it's executing, you can actually change the V-type. And this actually configures what really is a very flexible register file. So some of those things is the element width. So we can set the element width from 8 to 16 to 32 or 64, and plans to go even bigger. So the element is basically how much data do you want to operate on each vector element? So we'll take an example here of element width of 64. So basically we can put 4 vector elements in one of these 256-bit registers. Then there's a VLMUL. So this is actually the register grouping. You can group registers together. So you can, at the bottom there, 8. You can take 8 of those registers and make them 1, or you can actually, so that the 32 become 4, or you can actually go to partial. So if you use 1/8 mode, you could get 8 times 32 is 256 registers. So in this example, we'll set this to 2. So now grouping two registers together, we basically can have 8 elements in each register. So once this is set, every vector instruction is going to be working on 8 elements because you've set this. But you can change this as you run through the code. You can reset this type vector. If the nature of the vectors you want to operate on change, you basically reconfigure the vector file. So we'll run an example here on the bottom left. I got vector instruction, vadd.vv. So vv means vector vector. So we're going to add 2 vectors together. I could do vs, add a vector to a scalar, or ss, add 2 scalars together. We're adding 2 vectors, and I've before this meeting, I preloaded these v0 with 4 integer 1s and v2 with 4 integer 2s. And what we're going to do, v0 and v2 are the source registers, and v4 is the destination register. We're going to add all of these using that ALU at the bottom. But there's only one ALU, but one instruction is going to automatically add each element together in serial to become 3. Uh-oh. That's not right. Someone screwed the ALU up. That's not a feature of the ISA. That's an implementation error, I swear. But actually, it's a joke. What we really want to do is take advantage of some of the parallelism here. So now I'm actually showing an example of you can implement the ISA many ways. So here I want to do 4 additions in parallel. So now I'm going to add these 2 integers together, and in 2 clock cycles, I'll get get the basically compute some 4 vectors together, or some two vectors of length 8 together in 2 clock cycles. So it kind of illustrated the power here of the configuration, dynamic configuration of the register file, but also, and this basically means one instruction set can operate with many different ways of many different hardware implementations. So we'll kind of take these to examples. So this is a slide from Sci5. So Sci5, Krista Asanovich basically created RISC-V and led the development of the RISC-V vector ISA. But you see there, kind of, what does RISC-V offers? It greatly simplifies software development across a range of vector processors. I think that was illustrated. Change of vector length, and we have a vector length agnostic architecture. So the same instruction set works on any length of vectors, and then you could dynamically modify that register behavior, and that actually creates most efficient computations. So you can change how those registers behave to match your application, and therefore handle a broad range of applications. So to illustrate some of the flexibility, Sci5 offers 2 classes of processors with vector processors, their performance series and their intelligence series. And so you see here, the performance series got a 256-bit register vector unit, and then the intelligence series has 512-bit vector units. So this shows an example of one ISA, one set of programs, different configurations. Then a key thing here about RISC-V is they've added extensions to these. They have 5 Sci5 intelligent extensions. That's one of the beauties of RISC-V, that you can extend it. But the base ISA is there, and it's going to be constant, but you can actually differentiate yourself as a company by building on that with your own extensions. So another company, Andes, they were important to the RISC-V ecosystem. They're based in Taiwan. They had their own ISA, and when it was decided to come up to the new 64-bit architecture, they said, well, let's choose RISC-V. So Andes has actually gone from their own proprietary ISA to RISC-V, and they have a vector processor called the NX27. So kind of make the same points here. You can extend it. So you can, with the ACE extensions, a standard interface, coherent, cache coherent interface, they can extend their vector processors, and then just like Sci5, comes in many different flavors. You can tune the vector length, and you can tune the power of your processing unit. So, many applications vector processing applies to, so matrix multiply, FFT. So cryptography is an interesting one. So in fact, RISC-V has a crypto spec for scalars, but they're working on a vector crypto spec, which is going to take the RISC-V vector ISA and add some crypto extensions to massively accelerate crypto using the vector extensions. So it's kind of putting into practice what I already talked about. So I like this slide a lot. It's basically my slide. On the top is the cloud computing, and the bottom is the endpoint. The middle is the edge. One ISA, one processor architecture can be tuned for each of these domains. So here they're using 128-bit data path for the endpoint, all the way up to 512 in the data center. So kind of just illustrating both my initial point and the beauty of the RISC-V vector ISA. All right, so switching to emerging patterns, I'm going to take you through a couple examples. This is a product from Xilinx. It's called their Versal AI chip. It's their flagship. And kind of up there, you see with their AI engine array. And so if you look at that, that's basically a 2x2 matrix of what they call AI engines. And then if you drill in a little closer to the AI engine, you'll see that it includes a 32-bit scalar processor and a 512-bit fixed point and floating point vector processor. So a 2x2 array of vector processors. Well, are they the only ones doing that? This is a pretty fascinating company here called Graphcore. They have something called the IPU, the Intelligence Processing Unit. This is 1,216 elements, and this, again, a 2x2 array. Drilling in closer, what is that? Well, it's a local memory and a core, which is a 512-bit data path, 16 single bit per floating point ops per cycle, 100 to 1.6 gigahertz. So that's 25.6 gigaflops per core, or 31 teraflops per IPU. And you could take this to extremes. If anyone's heard about Cerebras, a startup that but their chip size is the wafer size. So they have 850,000 cores in a 2x2 array. If you drill down there, I don't know the data width of their processor. I know it's optimized for sparse matrix processing. but a fascinating technology from Cerebrus, but I think illustrates the pattern that I've been talking about. So looking at a company called Esperanto. So they're a part of RISC-V International. And if you look at upper right there, that looks familiar. It looks like a 2x2 array of something. Before I get into that, just a little bit about Esperanto. So the reason I'm here today is I forget the year, it may have been 85. The paper came out, the case for reduced instruction set computing, started a whole revolution, which industries are built on. And Dave Ditzel was one of the authors of that paper, along with Dave Patterson. Dave founded Esperanto. So looking at that, inspecting that 2x2 array, what is that 2x2 array? Well, there's 1,088 RISC-V, 64-bit RISC-V processors. Then each is attached to a vector tensor unit, illustrating the point again. In addition, on this chip, they also power it with 4 high-performance 64-bit out-of-order RISC-Vs on this chip. So this kind of illustrates, RISC-V lets you innovate. Where Esperanto is really innovating, actually, is in the power. Their chip runs on the x-axis you see there. You can run it down to, almost 0.2 volts. So you can run. If you want maximum performance, you can operate your chip at 0.9 volt at 275 watts, lower voltage at 0.6, but it actually runs down to 0.3 here. And you got 8.5 watts and 6 chips gives you 45,000 inferences per second. And kind of the optimum, throughput and power, here's 6 chips, 20 watts total at less than 0.3. So a lot of capability, but they innovated where they mattered. The real innovation here is actually in their energy efficiency. So, look at again to kind of make that point again. All their instruction encodings follow RISC-V vector conventions. So that they produced this chip before the vector spec was out there, but you see there, it's got the vector operations that are actually part of the RISC-V vector ISA, but then they build their own extensions on their tensor operations and cache control operations. All right, kind of tying it all together. So in 2017, proud to say a colleague of mine on the board, Dave Patterson, won the Turing Award, along with his lifetime collaborator, John Hennessy. And their paper lecture was called A New Golden Age for Computer Architecture. And notice security is on there, but we focus here as domain-specific hardware and software co-design. They kind of illustrated the point here where you show Python on the top going down to Intel AVX, which is Intel's vector instructions. But as you move from the bottom to the top here, what you're doing is making the software developer more productive. But the software is actually accessing more hardware. So, as you move down further down the stack, the hardware is getting more and more productive. And so they introduced, there's a layer now on top of these languages that came out like Python. They now have what are called domain-specific languages, such as TensorFlow, that are built on other languages to add another layer of productivity that's available to everyone. So to me, kind of ushering in the future and the framework that we're talking about, it's really about bridging between these domain-specific languages and domain-specific hardware, and how that's going to be achieved. So, I think there's 2 things. You want to enable the flexible and fast creation of the DSAs, make this hardware quickly, this new hardware quickly, and then you ought to easily be able to target the DSL or a new DSL to the new DSA. We want a kind of a virtuous cycle where both of these ends of the stack are improving. So you take those requirements there. how are we going to do this? One is leverage open standards to enable sharing between developers and domains. Then we want to actually create DSAs by connecting and configuring well understood kernels of productive hardware. So we don't want to rebuild these DSAs from scratch. We want to create kernels that are kind of elevated to building blocks for these DSAs in a manner that both the hardware and domain architects could understand. So here I've kind of hooked them up as a graph, but 2x2 arrays work nicely as well. And then modify or create new DSLs to target this new DSA hardware. So this framework for the golden age of computing, first, I think there is not a productivity problem. There's lots of languages coming out that are helping people in all kinds of domain. I don't think this is the problem of getting new domains specific languages. But down here in the hardware, first of all, here, back here, I notice I fixed Dave's slide, replaced the AVX with the RISC-V instructions. But we do need help here. So we need more investment in hardware. I mean, to me, that means hardware startups. We need open hardware standards. RISC-V is definitely part of that. And then we need, ways to, major reduction in the time and cost to develop this new hardware. And we need more hardware engineers. We need to make hardware cool again. Everyone likes doing software. We want people to be doing hardware. Interestingly, in Taiwan, I think it was 2019, I was on a panel and it was tweeted out during the panel, make hardware cool again. That's what RISC-V is all about. And the magic of the internet's, 5 minutes later on WeChat, I was quoted, and Rocky came through with me, and we've got hats for making hardware cool again. So that's the hardware, but then in the middle, we do need more focus on compiler technology. So actually, these slides I drew from the presentation I gave in 2019, but it's still relevant today. It's aged well. In fact, on February 22, Elon Musk tweeted out in response, compilers can be way better too. Not enough effort spent there. So when smart people agree with me, I'm not too proud to point that out. Speaking of smart people agreeing with me, Chris Latner, who created LLVM, which revolutionized compilers, actually gave a talk. He was at Sci-Fi called RISC-V and the Golden Age of Compilers. He's delivered this talk in version of this talk many places, but I was honored to have him at our My5 virtual summit last year in 2021, and he gave this talk. And it's not a 2x2 array of a parallel compute. He actually has a tensor of parallel compute. But how are we going to target or make this hardware actually productive? And so DSA compilers to the rescue was his point. And so he mentioned founded LLVM, but LLVM Foundation has a effort now going on called MLIR, which is basically multi-level intermediate representation. So this is now, instead of just compilers targeting scalar computers, they want these compilers to target this new generation of DSAs and actually help create those DSAs. So his concluding slide, I think makes all the points I'm making today. The pervasive RISC-V CPU ecosystem drives fundamental software. So, use the RISC-V like you saw Esperanto doing, the 4 controllers to control the chip. And then the RISC-V vector as perfect platform for the parallel compute. So use those RISC-V vectors everywhere and then extend them further with additional capability as needed. And then, the MLIR compiler system will tie it all together. So you can innovate where it matters. All right, so getting to the call to action portion here. RISC-V, this is a slide from Mark Himmelstein, basically asking people to help contribute to RISC-V. And you have something called development partners. So you see the Chinese Academy of Science, Rios Labs, and IIT Madras all have these partnerships between professionals and universities, helping lift the RISC-V ecosystem. So we have opportunities. If you're a professor out there who wants to partner with industry, we are trying to recruit you to help us with compilers, hypervisors, application libraries. So finally, Microchip has 1,517 openings, not including the ALU verification. Please attend the Mi-5 Virtual Summit. Promise interesting keynotes such as Chris Latner. And if you don't like fans, check out PolarFire, FPGA, and SoC. All right, I think that's it. I hope I'm on time. But if there's time for questions, let me know.
Wow, Ted, that was both extremely informational and I find it very entertaining. I love when you make hardware cool again. Like cool is double meaning, right?
Yeah.
I mean, because you talk about putting fan suppliers out of business.
I haven't even noticed that. You're right.
Here we go. Here we go.
Maybe turn into blue hats. Make them blue hats. People.
Yeah. So first of all, as we mentioned in the intro, you have 35 patents. That's 35 more than I have. It's just very impressive. In the recent past, CASPA had an honor to invite the CEO of Xilinx, the CEO of companies like Acronix, to be our speakers, and it's very fitting to have you from Microchip to talk about FPGA and RISC-V related topics. So thank you for coming and sharing with us. So for our audience, if you have any questions for Ted, first of all, the second half of this today's event is a panel discussion. So there will be a more lively exchange, Q's and A's. And also feel free along the way, post your questions in our chat, right? So, that maybe we can respond to your questions during the panel discussion as well. So at this point, because of time, Ted, just very quickly, especially you have a very impressive academic background, and you're talking about making hardware cool again, and encourage young people to go into hardware, not just software. For the younger people among our audience, what advice do you have for them if they want to pursue the career that you were talking about, whether it's in Microchip or just hardware RISC-V related careers?
Yeah, so RISC-V definitely is a big part of it is the academic thrust. I mean, it's founded by preeminent hardware architects, but it's global, and whatever country you're in, I definitely should take one computer architecture class, and chances are really good at this point that it's going to be RISC-V. As far as the hiring climate, definitely there's huge need to hire people in hardware today, and I think people are trying to figure out how to accelerate the advancement of people coming out of school. So pair them with just like RISC-V International has created these development partners where we partner with universities and people in industry to help lift RISC-V. Companies are doing that as well. So it's a great opportunity for college students to look into hardware, and definitely lots of exciting things in hardware.
Great. Thanks, Ted. My son is, a freshman in college. He is into software, so I will definitely quote you next time I talk to him.
All right.
So, right on.
Yeah. All right. Thank you. Sorry for running late.
No. Thank you, Ted.
All right.
Yeah. So
Okay.
before I jump into our second speaker, allow me to take a quick commercial break. I would like to invite our president of CASPA to give us share a few words with us, regarding our CASPA organization. So at this point, please help me to welcome Charlie Zhou Haohua.
Hello, thanks, William. Can you hear me?
Loud and clear. Yes.
Okay, great. Yeah. So good afternoon. Yeah. And I'm Haohua Zhou, President and Chairman of CASPA 2022. And before we deep dive into the symposium, so let me allow me to make some introduction about CASPA. On behalf of CASPA, I welcome you to attend this symposium. Thank you for support. Thanks for volunteer and speakers' preparation for make this happen. So we are very glad to see the pandemic is under control and the whole US is on reopen stage in the spring. So our spring symposium is CASPA's signature event for almost 30 years. Some of our audience may be familiar with CASPA, but some may not. So I would like to take this opportunity to make some introduction about it. So for my CASPA old friends, please take it as a memory reflection. CASPA is an international volunteer-based non-profit organization founded in 1992. Over the 30 years history, and we already built like 12 chapters, 7 are in US. So we have more than 60 corporate sponsors and 7,000 members. So CASPA mission is bridge, connect with sponsors, members, and volunteers. So our number one mission is promote technology innovations like this spring symposium. So we have all these signature events, like public events, and also invite-only events for sponsors and members. So over here, you can see we have conference, symposiums, special seminars, job fair, career development seminars, entrepreneurship events, financial and law seminars, also have science and engineer fair and related education day series. As a tradition, CASPA have an annual conference where you invite all the executive keynote speakers from influential semiconductor companies. So we're already including companies from EDA, FPGA, and equipment, and all the semiconductor components company and IP companies. So as a heads up, this year we'll have ARM CEO to make a presentation in this October. And CASPA have before pandemic, we host a conference and symposiums in Santa Clara Convention Center or in some venue. So we invite very influential speakers, also have a lot of audience. So this example shows last year's annual conference. And also we have career development, job fair. Last year we host online. And also we have career development seminars for our members. And we have executive networking events too. And as US go to reopen, so we are going to host some online event in the coming couple of months. And we have financial and law seminars for help our members to better help on the financial life, and also about the startup company, when the startup company, the legal issues, we'll have seminars happen. So we have business delegations, and also we have educations for youth. This majority is for our members' kids. So we are going to have a science and engineering fair in this summer break, and they are going to have couple events, and we'll post on CASPA.com. And also we have a scholarship for our members' kids. And I welcome you join CASPA. Either invite your company, join as a sponsor, and individuals join as a volunteer. Also, you join as a member to receive a member-only benefit. So, as a 30 years history nonprofit organization, we have our own publications, and over last 30 years. So we have proceedings, and also we have e-letters, and to social media, we have linking and the YouTube channel. And you can check out Join CASPA YouTube channel for technology-related topic. Also, we have CASPA e-talk. It's more related with the educational and the member-related events. So as the sponsors, there are a couple of benefits as a list here, and you can check the details on CASPA.com. And individual members, they have a member-only benefit. Especially, you can download all the PowerPoint and the PDF, the past PDF from our website. So also welcome you join as a CASPA volunteer. So as you know, all our event is hosted by a volunteer, and you can build up your leadership capabilities, and also networking with the peers, and do community service. We know, like in Silicon Valley, we quite friendly, like change jobs over company. But in CASPA, you can always see your old friends. So as a special thanks, we have, not only this special event, we have Invest Hong Kong, for this spring symposium. We also, like annually, we have all these sponsors sponsor our, every event. With that, and thank you, and I will, welcome you to join CASPA, and you can scan the barcode here, like either on the website or WeChat or LinkedIn or Facebook. And with that, I will give back to our speaker, William. William, to this.
Thank you, Charlie. Under Charlie's leadership, CASPA is getting bigger and stronger, and together as a team, we are able to put together a program like this is Spring Symposium today. So thank you, Charlie. Okay, so now we are done with our commercial. Allow us to get back to our program today. Our next speaker is Rob Maines. Rob is a 40-year industry veteran and currently the general manager of CHIPS Alliance, which is part of the Linux Foundation. Rob is a former engineering vice president of Oracle and distinguished engineer at Sun Microsystems, where he led an organization of over 200 software researchers and developers. Prior to that, Rob was a principal engineer at Magma Design Automation and originally a senior engineer at IBM, involved in numerous technical areas for the development of IBM Power and S390 systems. Rob has in-depth experience in software development, electronic design automation, IT management, semiconductor technology, microprocessor circuit design, and chip construction methodology. He is the holder of 13 US patents. The title of his presentation today is Accelerating Time to Market, Open and Collaborative Innovation in the Hardware Development Ecosystem. So Ladies and gentlemen, without further ado, please help me to welcome Robert Maines.
Thank you so much, William. It's a pleasure to be here, and thank you for the honor to be able to present to folks today. So hopefully that shows my starting slide for everyone. So this is a new area for me in my career, which is in the arena of open source hardware development. And as my colleague Ted Spears just previously mentioned, we are seeing a rapid innovation in the overall hardware development ecosystem. It's really a change from what has been historically in the past, I think, as everyone knows. So I will talk a bit about that and then draw parallels to what we saw in the software ecosystem by comparison and how they have very much similarities between the two. So as William mentioned, I have about 40 years of industry, and if you can see here in my background here in my office, I have a chart that says keep calm and carry on. And that was my motto when I was in charge of design enablement at Oracle. And I think as everyone here knows, working on the latest semiconductors, it does require a degree of calmness, if you will, as well as humility, because we know that the stakes are high and the opportunities for failure are quite often. So both humility and calmness are two important parts. But that said, it's been very interesting career. Like Ted, I started in upstate New York with my education. I have a bachelor's in electrical engineering from Union College, actually, which is not too far from Cornell, and then a master's in computer science that I got courtesy of IBM and National Technology University. But I want to say this one thing, that over the years of observing this, that a change is the name of the game. Things are always evolving. There's always something new. And generally speaking, it's always improvements. So if we look at the history of computation, if you will, it's really more than just Moore's Law. Of course, Moore's Law has provided us with tremendous benefits in terms of allowing additional capability to be put onto a single chip with greater performance, less power, less area. So that has really enabled much innovation. But that's not only the aspect of it. There's also in terms of what's happened in packaging. If we go back in time with the multi-chip modules that first came out in the late 70s, early 80s, and continued to this day, to now the AIB or chiplet type of protocol that Intel originally was one of the innovators in, but then also has had quite a bit of contribution from AMD and others, and there is a new collaborative effort on that now. We just heard about domain-specific computing, and that's very much true. We're seeing that in my final years at Oracle. We developed a database acceleration unit that would specifically accelerate queries to the Oracle database. And of course, that was captured through the architectural analysis of calls that were made of commercial workloads to Oracle database, and to see how we could actually accelerate that. So a key backplane to this entire picture here, which I don't really talk about in the chart, but is really the underlying computer architecture. That really is the inherent aspect of any of this work. And if the architecture is not right, it's not going to make really much difference as to how good the process technology is, how good your time enclosures, et cetera. If the architecture isn't right, there's a fundamental problem that you would have to do. In any event, accelerators and domain-specific type of execution are becoming a real thing. And then also, as mentioned just now too, software. The compilers and the libraries are key aspects as well. I know when I was at Oracle, a key challenge that we had was that the Java runtime libraries were not optimized for SPARC microprocessors, but were optimized for x86. So that was a real hindrance in terms of the performance of the SPARC processor to the end customer. The chip itself was fine, but the libraries were a problem. So that was an item that had to be taken care of. But there's something new in the front here too that I want to chat about a little bit about. And that's really going beyond all the typical technical accelerators that we see. And what that's really is talking about how industry is changing. We're really going from a siloed type of model that we have historically seen in the past to more of collaboration. Now, with recent events in the world, as we see, it's hard to say exactly where this will shake out. But if we look back in the past, we can look at large companies like IBM as an example, or we can look in the automotive industry, such as Ford or General Motors, where everything was done in-house, from owning the rubber plantations to make tires, to owning the mines, to mill the steel or coal, to actually help build that into motors. Or in IBM's case, as an example, it's also true for the original AT&T, that it was all the way from process technology up through the design, through the software to build the entire product. Everything was there. And then we've migrated more to what I call supply chain management type of thing, or just-in-time delivery, where a given company will rely upon different partners in the industry, whether it be a foundry provider such as TSMC or Samsung or Global Foundries, or to some of the major EDA companies to provide the necessary services for your company to build its given product. To where we're now moving to what I call more of an open collaboration environment, where different companies are coming together along with universities and individuals to collaborate on different products and problems in a collaborative fashion. And what this really boils down to, aside from accelerating innovation, is also modulating the R&D spend and the NRE costs associated with building product. So it's a change in how we've been doing things in the hardware arena. But this is not necessarily a new idea. If you look at software, it has evolved quite a bit. So years back, there were punch cards way back in time. Code was written in an assembler. It was even written in Octal, right? When I first started my program in studies years back, I had a mini computer that I had to write code in using Octal, which was an interesting, right? Flowcharts, line printers, etc. More modern evolution, if you will, comparatively speaking, would be VI and Emacs or DBX and GDB. But now if we look at it, it's really a lot of fun to be a software developer, right? And that's in part, I think, the challenge we need to solve as from an engineering perspective for hardware engineering. But for software, right, everything's object-oriented. There's a lot of productivity tools. You can write it once, it runs anywhere. You have reusable components to pick from to build what you want to do. Tons of library available on demand, just magically goes out and finds things for you. And it just makes it, just a pleasurable experience. So what this is really all about is accelerating innovation, increasing productivity, and doing it with less resource, right? So it just makes life a lot simpler. You pick up components, they work, and it saves you a lot of development time on yourself. And so from a historical perspective, you also may recall that back in the early 90s, there were a lot of different operating systems, right? Some may recall VAX CMS from Digital Equipment, right? There was HP-UX. There, of course, is the mainframe operating systems from IBM, z/OS. One of my alma maters, which was IBM actually, and also Sun Solaris was still around, very prevalent, OS2. And then something came on the horizon called Linux. Of course, Windows was out there at this time. And I recall the first time I heard about Linux when a colleague of mine showed up in my cube and said, hey, I've got this new thing I'm playing with called Linux. It's kind of like Unix, but it's a bit different. And it's like, yeah, whatever, sure, I suppose it'll evolve into something. Well, sure enough, it did. So that now is comprised of the Linux Foundation. That's more than just the operating system that all of us pretty much in engineering use to build chips. It has about 1,500 members, participation from 40 plus countries, all of the Fortune 100 telecommunication and tech companies, 30,000 some developers are contributing code. And it covers a wide range of things from security all the way down to motion pictures. So there's just a wide swath of areas that Linux Foundation is involved in. So then the question is what about hardware? Well, we heard a little bit about that in Ted's presentation. RISC-V International is part of Linux Foundation, as is Open Power. And CHIPS Alliance kind of bridges both gaps. We cover different aspects of these things. I'll chat a little bit more about that. But hardware itself is seeing a huge, tremendous growth right now, right? In terms of 5G, advanced computing, healthcare, Internet of Things, et cetera. So by the year 2050, there should be over 100 billion types of different chips, which also is why we have a chip shortage in some regards too, right? There was pent up demand because of the pandemic, but the fact of the matter is just so many things in our daily lives have chips. I recently had my garage door opener replaced, and the reason it was is because the chip in the motherboard in the opener blew, and the cheapest thing to do was just replace the whole thing. So lo and behold, that's what we did. But that's just an example of where your silicon is these days. So the open hardware growth has been tremendous, as Ted was mentioning, and CHIPS Alliance is part of this with RISC-V, and you can see this, right? That the amount of participation in RISC-V has grown tremendously over the past 5 or 6 years, right? CHIPS Alliance itself is a 3-year-old organization, has 37 members to date, and is active participation and growth. So we cover many different areas aside from a particular instruction set, we cover things such as implementation, open source tooling, open source PDKs, verification suites, etc. And just to give you one more example of the growth interest in RISC-V, it's up to 62.4 billion cores are projected by 2025. And of course, Ted already mentioned about the investment that Intel has made in that, which is an important aspect. So CHIPS Alliance really is fundamentally about building an open source design ecosystem, right? All the way from specification, RTL, process design kits, tooling, the actual physical implementations and standards. And this would really allow us to create a broad open spectrum of innovation across that. Now, one of the things that you may ask is, well, why are open source PDKs such a big deal? Well, here's the thing. For those that are knowledgeable in building chips and dealing with semiconductor manufacturing companies, PDKs are an inherent part of the ingredients of what they do to actually build the chips. And typically speaking, you have to go through a long legal negotiation process and sign a non-disclosure agreement. But having open source PDKs and not requiring documentation, legal documentation to be signed relative to non-disclosures really opens up the ecosystem of innovation and allows for different companies and universities to come together and collaborate on a particular problem area. So it really simplifies and solves a problem. That doesn't mean to say that companies cannot come together on proprietary things as well, but it just has additional levels of challenge because of the legal underpinnings involved in doing that. Another key aspect of trying to help move innovation, of course, is enabling design, reuse, and interchange. That could be in the forms of soft IP, such as logical macros that are synthesized through electronic design automation tooling to a particular target technology the chip is in, to hard IP that could be commercially licensed or could be provided by via open source that you can then just place in the particular chip technology they're trying to do. And then chiplets, as I mentioned earlier, is a newer concept of having small chips, as you see in the photo there on the right, that are comprised of different types of IP that you might pick up. And I have another chart on that a little bit further down the right. But the basic idea is that you can pick up IP in a catalog, whether it be open source or private, know that it's good, and use that to build silicon for your product. So let me just talk about a few examples from CHIPS Alliance. So as I just had mentioned, the AIB interface, and here's a little bit more detail, but effectively AIB provides for an electrical protocol for different chips or chiplets to connect with each other, a standardized interface. And that takes a lot of the engineering and electrical work out of the problem set for a developer of another chip. So you can pick up a chiplet as an example from one of the menu on the right as an example, and then use that on a higher level package with your IP that you build, where you follow this protocol and then build the particular innovation that you're interested in. So it takes a lot of the challenging work relative to devising the actual underlying PHY layer and also the protocol as well. A project that we're trying to get going in CHIPS Alliance, a collaboration project, is an open source DDR controller. And we are in talks right now to help start getting this project going and use it as a collaboration vehicle to help show or demonstrate the power of open source innovation. We'll likely start out in an open process technology node, a more mature node, but then move it towards a more advanced node, say in 12 nanometer, sometime in 2023. So this is something that we're trying to do to help demonstrate the power of open source and collaborative development. And as was mentioned earlier too, we've been working with RISC-V on a cache coherency protocol known as OmniExtend. And really what it does or allows for is to allow for a collaboration or cache coherent collaboration mechanism between different types of CPUs. RISC-V showing here, could also be a GPU or an FPGA, AI accelerator, et cetera. But the idea is, again, is to come up with a standardized protocol that different members can participate in, and that's being done as a collaborative effort with RISC-V. The RISC-V Swerve core ecosystem, the Swerve core was developed by Western Digital, and the overall verification suite, along with the Verilator open source verification functional simulator has been provided to CHIPS Alliance to allow developers to pick up this design and then use it with the IP that they want to build themselves. And along with that, the system Verilog and also the UVM based random test generator suite has also been provided as part of this for verification of that to the engineering community. Let me talk a little bit more about EDA. So one of the things that we're trying to do, and I think this really kind of dovetails into getting more people interested in hardware engineering. So for those that have gone through the engineering education, I've also experienced it professionally. Engineering is a hard field. I think there's no getting around it, or I'm not going to try to mince words on that. But I think there are things that we can do to make it more attractive. And a lot of this has to do with, aside from understanding the low-level details of transistors, as an example, which originally was a hand-tuned, hand-placed and routed type of thing, and understanding all the electrical effects below that. And then we migrated in time to gates, or our first level abstraction, and then into more of an RTL type of approach, which has been the most recent usage typically. And I would say that's a little bit more like writing an assembler. For those of us that have had that experience, writing an assembler is certainly a noble undertaking, but I cannot say it's necessarily fun. Similar to RTL, right? So a more fun approach is to write it in a higher language. It's more of a software approach, whether that be Python or some type of object-oriented based language that has offered with it libraries of services. It's easy to use or easy to reuse and has integrated verification associated with it. And then we have a set of tools that basically compile it and spit out, if you will, gates or transistors that can be used to help move that. So the overall idea here, aside from making it fun, is to accelerate innovation and increase productivity with less resource, similar to what we saw in the software arena. The other thing I want to say, and this is kind of an interesting thing, is what I would say is changing culture, which is overcoming the fear of failure. So for those that have been through chip tape outs, it's a multi-year endeavor. Usually it's very expensive to tape out a chip. There's a lot of engineering time and effort used to do that. So I make it kind of akin to, it's like launching a mission to Mars, or if you've seen Apollo 13, you know what I'm talking about when you see the folks in mission control waiting for the launch to happen, right? It's basically all systems go. And it's kind of a result was a paranoia, a fear of failure. So not to quote Andy Grove here, but maybe the paranoid only do survive, right? But that's really kind of the mentality that typically exists in engineering, right? And particularly for modern processes, right? Where it's, as I said, it's a multi-month effort and it's a multi-million-dollar undertaking. So, we're really trying to change that, right? Remove that failure is not an option type of paradigm to allow for more tape outs at low cost and older nodes. And that certainly is, what we've been seeing in the case with both what Skywater has offered and eFabus, is to be able to do that type of thing, right? And so this is kind of similar to what we've seen in commercial space launches like SpaceX Blue Origin, right? To make it more common and make it easy. The other aspect, of course, is to make hardware more like software, right? So that again comes into providing different language choices that folks can use, whether it be Python, System Verilog, System C, Chisel, which is an object-oriented language based upon Scala. It really improves the designer productivity and simplifies the overall thought process. It allows for libraries of functionality to be used to help build what you're trying to do. Encourages object-oriented thinking. And I believe this will help encourage broader participation by the community, not just your traditional hardware engineers, but also software engineers who are really interested in understanding how this all works. And then high-level synthesis to actually go then generate the RTL. And then you have implementation tools that will help to realize it into gates and transistors eventually in layout, and effectively rely upon those to provide guardrails to help guide you, if you will, to a safe landing for the chip that you're trying to design. I mentioned this earlier, but of course we have extensive effort or collaboration in the area of open source verification with UVM and Verilator, Verilator being an open source event-driven simulator that is used extensively for design verification. And another important aspect, of course, is to be able to prove and design more quickly. So as I mentioned in the earlier chart of providing guardrails, there is quite a bit of effort relative to being able to synthesize a design or to generate analog circuits with some type of generator. And there's a number of different tools, open source tools that are available to do that. Another key aspect, of course, is source verification and doing this in a rapid fashion. Being able to map a design onto an FPGA allows for much more extensive verification of that design before you actually tape it out and then receive the silicon back. So that allows for much quicker verification, less expensive verification as well. So specifically on digital implementation flows, the US government has funded a program called Open Road in conjunction with University of California, San Diego. And this is your traditional, if you will, digital implementation flow from logic synthesis all the way to layout, including timing and power analysis as part of that to ensure that the digital block does meet the objectives of what you're trying to do. There's also work in the analog area. So you'll see here the analog work group mentioned. CHIPS Alliance has a number of different work groups involved that collaborate on different topics, from FPGA to design languages such as Chisel, for example, to analog to digital implementation. So we are working with a number of universities on different solutions in the analog design space. Automating analog is a challenging arena. This certainly will help also to broaden the ecosystem of participants in this world, because they don't necessarily have to know all the fine details required for analog design. We also have efforts in terms of the FPGA interchange format. So this idea here is an open source effort to provide a common interchange format for different FPGA suppliers and application developers to write to a common interchange format to allow for exchange of information of FPGA design in open source fashion. This was originally donated by Google and is now part of CHIPS Alliance, and we're helping to move that forward. So to put this all together, I know I've covered a lot here. What we're really trying to do is to build an open design enablement ecosystem with a catalog of trusted ingredients. And that could be a trusted IP component library, could be an open source cell library, could be different macros, physical macros, and different types of tooling as well, as including also the verification test bench as you've seen on the left. So there's quite a bit here, and we have work to do to bring this all together, but we are making progress. And so what this is really all about, it's about building trust. It's more than just having an open source IP or application catalog, right? You need to have confidence to know that what you are getting from it is giving the right answer and it works, right? Software has built this in its community over many years with discipline. And one key difference between hardware and software is the fact that the confidence in the underlying design or technology can vary between the process nodes involved. So in other words, a circuit or a logic or physical block that may work at 20 may not work at 7, right? Because the underlying physical effects has changed. So your applications or your software applications used to design this has to update that accordingly. Relative to hardware IP, of course, you want tape out, productization confidence, you want to have a prevalence and availability of cheap shuttles available to help you prove these things in to make sure that they are work. And of course, for EDA applications, regression testing and quality results are key parts of the development process. And qualification of the foundry data is a key aspect as well, right? So does it correlate to the extraction? Does the timing correlate, et cetera? Are the DRC rules correct as well? So there needs to be further work in terms of building collaboration bridges between foundries and open source EDA applications. So to sum it up, what we're talking about is building an open source model of IP and innovation to help build your product. Really to have a trusted open IP catalog that would allow you to add your innovation on top of that to build a product that you are trying to take to market. And then putting this all together, it's really an open IP community and a business services type of model, right? Similar to what came about with the Linux operating system. Companies such as Red Hat were formed that help foster a developer community, and then have service companies such as Red Hat that could put this together into a product that is built and supported for end users to use. So in conclusion, open source hardware verification tooling are here. They're gaining momentum. It's growing quite rapidly, as we are seeing. hardware engineering is learning from software, abstraction, object-oriented design, libraries of functionality, things becoming a reality that help ease the burden of learning how to do this. And companies and universities are collaborating on mutual challenges of interest. And as I just mentioned, the business models are moving forward to help embrace this. And companies are innovating at higher levels, leveraging open source IP, accelerating time to market. The CHIPS Alliance, as part of the Linux Foundation, is a venue to provide a collaborative opportunity for all to participate. So with that, I will stop. Thank you.
Wow, thank you, Rob. That's leveraging 40 years of experience. That's thank you so much. That's and part of that is just a very nostalgic, right? You talk about punch card, OS2, mini computer. Reminds me my days in IBM Rochester, where we support the wire and network protocol microcode using a language called PL8, which I believe was developed in the East Coast, IBM out in New York somewhere. You probably know that better than I do.
Yes, I'm familiar with that.
So yeah, so again, we welcome our audience to post the questions in the chat. But just real quick, especially you talk about making things easier, getting more people involved, right? In particular in the EDA space, it was very intriguing, like using Python for RTL, for example. So what do you think? When you talk about that, what's the reaction? And what's the impact on traditional EDA companies such as Synopsys and Cadence?
Well, I think when I talk about these things or mention these, people are excited about that. They're interested in different ways of thinking. But I will say it depends upon the audience that you talk to, right? So, there are, how shall I say, the crusty individuals who's like, that'll never work. But on the other hand, and crusty can apply to anyone. It doesn't mean any specifics, but there is a definite problem if you chat with professors at leading institutions. So I chat with professors at Berkeley, at Stanford, UT Austin, just to name a few, right? But there's a real challenge in getting students interested in learning about hardware or electrical engineering. And so I think by being able to describe designs in a higher level language, such as Python, which is kind of the popular language right now, that will greatly improve that. If you hand someone basically a Verilog manual as an example, their eyes are just going to glaze over. It would be akin to me handing you, a mainframe assembly programming language book, right? It's like, you got to be kidding me, right? So, I mean, not that there aren't needs for that, right? But there are better ways to do things, more productive ways and more fun ways. And then I think EDA companies are trying to address that. I mean, one of the members that we have in CHIPS Alliance, that's an EDA company, Siemens specific, I'll mention it since it's public record, but they're very interested in what the open source community can do, right? And I think also in terms of how different design languages can be utilized or advanced to help improve productivity for folks.
Yep. Great. Yeah, hardware is hard. So Rob, please keep up the good work. We all need to find ways to get younger people involved by kind of lower the bar just slightly a little bit. So keep up the good work.
Thank you.
Yeah, and thank you for your time. So yeah, we're going to see Rob again during the panel discussion. At this point, let's move on to our next speaker, Dr. Hui-Ming Bu. Inviting our next speaker, Frank Zhou. Frank serves as the Vice President of ARM's infrastructure line of business and is responsible for business and ecosystem development in the Chinese market. He leads the team to continuously innovate ARM IP products and solutions to meet the needs of the Chinese market, from cloud data centers to the edge infrastructures. Before joining ARM, Frank Zhou was the CTO and the VP of Huawei's Enterprise Business Group in the US. Frank has more than 20 years of industry experience in Silicon Valley and has held positions such as software engineer, platform architect, and product management director at companies like Cisco, Juniper, and EMC. Frank holds a master's degree in electronic engineering from USC and a bachelor's degree in electronic engineering from Peking University in China. The title of his presentation today is Evolvement and Trend in ARM's Cloud Infrastructure Ecosystem. So without further ado, ladies and gentlemen, please help me to welcome Frank Zhou.
Thank you. Let me bring up my slides. Can you guys see my slide?
Yes, very clear.
All right.
Thanks.
So good afternoon, everyone. This is Frank Zhou from ARM. I'm the VP of the go-to-market at ARM's infrastructure line of business. Today, I'm very happy to have this opportunity to attend CASPA Symposium 2022 and share some of my thoughts about the mega trend in the semiconductor industry, especially in the cloud 5G infrastructure space. AI, 5G, and the Internet of Things are all maturing at the same time to create a new computing landscape we like to call the fifth wave of computing. It will fundamentally change the world we live in and enable great efficiency and a more sustainable world. If we consider the vast amount of IoT endpoints that now outnumber the number of people in the world, these devices need a global network with AI-enabled compute capability woven seamlessly. We see devices like IoT gateways, edge compute servers, and even 5G networks becoming smarter and adding more compute resource at the edge of network. ARM is powering these next generation infrastructure designs by providing the IP necessary to scale compute costs from tens of cores in a gateway to thousands of cores in data center rack. Also, cloud native software and technologies like virtual machines and containers, which can run natively on ARM 64-bit architecture, are also being adopted throughout this infrastructure, bringing a new level of compatibility across the whole ecosystem. Here is some data from the Synergy Research Group I would like to share with you. It shows that Q4 2021 enterprise spending on cloud infrastructure service passed $50 billion mark, up 36% from the fourth quarter of 2020. Total year spending reached around $178 billion, up 37% from the year of 2020. Amazon continued to lead the market with its worldwide market share staying almost constant around 33%. In the meanwhile, Microsoft continues its market share growing by almost 9% points since the end of 2017, reaching 21% in the fourth quarter of 2021. Google and Alibaba also continue to grow market share, while in aggregate, the long tail of small to medium-sized cloud providers see revenue growing steadily, but market shares declining. On the right side of the slide, the diagram shows the growth of infrastructure spending. We can see actually telco capex level up to the first half of 2021 were once again flat, while the hyperscaler operator CapEx shoot up by another 30%. Meanwhile, enterprise spending on IT infrastructure recovered a little bit and grew by 6%. These numbers reflect the longer-term trends, which show that telco CapEx has essentially been static for the last 6 years, while hyperscaler operator spending has almost tripled, and enterprise IT infrastructure spending has grown by 23% as well. So the total infrastructure spending in the first half passed $300 billion mark, with hyperscaler operator growth accounting for 27%, up almost from just 30% in 2016. We can see it's just 13%. So ARM is the world's leading semiconductor IP supplier with more than 600 silicon partners. And our partners combine ARM IP with their own IP to create complete chip designs. Our technologies secure power products from the smallest sensor to the most of the world's smartphone and even the world's most powerful supercomputer. Our energy efficient processor designs and software platforms has enabled advanced computing in 200 billion chips shipped since ARM's inception in 1990. And also the pace of the shipment is accelerating, as last year alone, over 23 billion chips shipped with ARM-enabled technology. Together with our ecosystem of technology partners, we are at the forefront of designing, securing, and managing all areas of connected compute, from the chips to the cloud. ARM Neoverse is a modern cloud-to-edge infrastructure foundation for a world of 1 trillion intelligent devices. ARM Neoverse is a dedicated roadmap and the new brand of infrastructure class IP for 5G networks and the next generation cloud to edge. And ARM Neoverse solutions are also uniquely designed for the higher levels of performance, security, and scalability not seen today. Innovation from microarchitecture design up through silicon, software, and system will enable best-in-class solutions to address the diverse and evolving requirements across the entire compute spectrum. And also the rich diversity of hardware and software solutions that have come to market enabled by Neoverse-based compute are now deployed in the cloud data center, HPC systems, 5G networks, and out to the edge gateways, providing cost savings, power efficiency, and compute performance gains. Back in September, when we introduced our newest Neoverse N2 and Neoverse V1 platform to our roadmap, it was a testament to the groundswell of Neoverse interest and adoption across our ecosystem. Today, I'm pleased to share some growing list of ARM partners bring the superior performance per watt, and the TCO benefits of Neoverse to the infrastructure markets. A couple of examples milestones in 2021 we achieved. For example, Marvell actually revealed its Octane family of networking solution based on Neoverse N2, and it will begin sampling by end of 2021, providing 3x performance uplift over previous generation of Octane solutions. And also Oracle plans to adopt Ampere Ultra CPUs for Oracle Cloud Infrastructure as a price performance leader across a wide range of workloads. ARM-powered AWS Graviton 2 continues to rapidly expand its EC2 footprint with steady growth and regional expansion. Look back to the in China market, Alibaba Cloud just tested the upcoming Alibaba Cloud ECS ARM instance, showing off impressive results on the Spec JBB benchmark, with Spec JBB, which is a Java benchmark, and it shows improved performance of the Dragonware JDK on ARM by almost 50%. Tencent is also making investments in both hardware testing and on software enablement that will allow them to adopt Neoverse technology for cloud applications. So it's not the news to all of us. AWS has been leading the charter when it comes to adopting ARM Neoverse for their infrastructure through the Graviton and the Nitro. They have come a long way in their effort to optimize and offer more and more EC2 services on Graviton 2 while enabling wider variety of workloads on them. Based on a popular analyst literature, of all the EC2 instance types added in calendar year 2020 by AWS, around 50% of them are based on ARM-based Graviton 2. And while the x86 make up the remaining half, which is pretty impressive. In December 2021, AWS also achieved its next ARM technology milestone with AWS Graviton 3, which delivers 25% more performance for compute-intensive workloads. Additionally, Graviton 3 achieved up to 2x floating point performance on machine learning, gaming, and media encoding workloads, and up to 2x faster performance on cryptographic workloads. Graviton 3 also supports the bfloat 16 data, bfloat 16 data to deliver 3x better performance for machine learning workloads. And all of this are achieved while using up to 60% less energy. Even more, AWS reviewed C7G instance powered by new Graviton 3 processors, and these are available in preview stage right now. C7G is the first cloud instance to support DDR5 enabled by ARM Neoverse platform to allow for more memory bandwidth and unlock even more performance. Customers like Twitter are already testing C7G instance in beta and seeing almost 20 to 80% of higher performance over C6G instance. Back in the China market, at the Apsara Conference 2021, which is an annual cloud service technology forum hosted by Alibaba Cloud, it announced an ARM-based server processor E10710, developed by Alibaba's in-house semiconductor unit, T-Head. The E10710 was built for custom by T-Head. It has 128 ARM cores. In addition, it also features a 3.2 gigahertz fast clock speed. Each processor inside it contains 60 billion transistors, as well as a 96-lane PCIe 5.0, and even eight DDR5 channels. E10710 was the first processor, Alibaba's first processor to have an ARM v9 compatibility processor. The data center would benefit from this development. According to Alibaba, the chip would be utilized to extend cloud service support for customers in the near future. Besides success at AWS, there are numbers of US and China hyperscalers who have publicly announced their intentions to deploy ARM Neoverse-based Ampere Ultra servers. Some of the noteworthy ones, including Oracle Cloud, which I mentioned just in the previous slides, and also Micro Azure, Tencent Cloud, Cloudflare, and ByteDance. The way Ampere has been positioning themselves for their ultra platform is for anyone who wants to deploy Graviton 2 type of compute capability on their premise data center. Also, a dedicated processor optimized for some certain tasks creates an opportunity for the customer to better focus their CPU cycles toward paying workloads instead of the infrastructure tasks, yielding TCO benefits in power and CapEx. Here comes with the DPUs. Some notable announcements included in this slide for DPU update. In July 2021, Marvell announced its Octane 10 family of DPUs built with ARM Neoverse N2 and TSMC 5nm process. Octane 10 promised to deliver 3x more performance and 4x performance per watt. And recently, also we see actually Intel announced its IPO codename Mountain Evans with the leading US-based cloud service provider, which is Google. It combines 16 ARM Neoverse N1 processors and other accelerators into a single chip, DPU chip. And also NVIDIA, in the meanwhile, announced that its Bluefield 3 DPU containing its Mellanox technology and 16 ARM Cortex-A78 processors will be able to replace 300 traditional processor cores. Samples are expected in the first quarter of 2022, and later, Bluefield 4 will double bandwidth to 800 gig bps. And also we see actually VMware, Dell, Cassandra Systems, Palo Alto Networks, Chronicles, Supermicro, NetApp, and others have launched products or initiatives to take more advantage of DPUs. Let's look at the HPC market. So HPC market is expanding with new type of work, adding AI and data analytics to those traditional simulation and modeling. ARM is a driving force behind many of the new exascale class CPUs that will power tomorrow's supercomputers. Let me first highlight Fujitsu's A64FX processor that powers the Fugaku supercomputer at the Riken Center for Computation Science in Japan. Fugaku made its debut and became the fastest supercomputer in the world ever since June 2020, as well as becoming the first ARM architecture-based computer to achieve this. Basically, it achieved 1.442 exaflops in HPL AI benchmark, making it the first ever supercomputer, and it still maintains this top rank actually today. They also maintain this top one even in 2021. And also European Cypher has developed its own Neoverse V1 based SoC, which features substantial HBM3 memory, along with DDR, and enable other EU accelerators in the future. And the ETRI is a national research institute in South Korea. It's developing an ARM-based CPU for their future supercomputer. It will support both double and mixed precision math to tackle HPC and AI applications. Finally, NVIDIA coming to the market in 2023 with their Grace CPU built with ARM Neoverse IP. According to NVIDIA, it's expected to deliver 10x the performance of today's fastest server on the most complex AI and high-performance computing workloads. They also announced 2 large-scale HPC design wins at Los Alamos and also the Swiss National Supercomputing Centers. That's a big win for ARM ecosystem as well. Let's look at the 5G market. We see 5G momentum and developments accelerating rapidly. Developments and time to market from the specifications is much quicker than we saw previously, with 2G to 3G and then from 3G to 4G. The rate of deployment is probably double what we expected and has somewhat taken the industry by surprise. Also, Arm's challenge in continuing to support the rollout of 5G is how we can help define and support scalable platform needs. Looking at some of the market size and some of our position in this market, cloud data center is the largest market. But for the traditional cellular equipment path, the radio access network is the largest, significantly larger than the core. Arm has a significant market share in the RAN, probably around 80% or higher today, largely because of our close relationship with those tier 1 networking OEMs and their silicon providers like Marvell, Broadcom, and Xilinx. Arm has also now joined many of the open initiatives like the Open RAN, right? O-RAN Alliance, and also FBTIP. And it will be interesting to see how quickly this market share grows for the open platform equipment. The 5G supply chain is constantly evolving, and Arm is collaborating across the industry, building a strong ecosystem that meets the various technology needs, but also looking at the various links to facilitate deployment of these technologies. 5G has brought a new set of user cases, which are significantly more complex and has new requirements, such as being cloud native. By generating a wider base of collaborations, Arm's desire is to support these new requirements, support the new stakeholders, and create more choice and diversity in this market. This diagram illustrates how this works. So basically, Arm will provide a silicon framework to provide flexibility in base platforms. Then we're working through silicon partners and into the tier 1 and emerging 5G network OEMs. We recommend the right blend of compute while integrating those accelerators for the L1 processing, machine learning, packet processing, or security into those SoC devices. And together with the ISVs, combine these SoC devices with the software implementations. Next, we'll ensure we are meeting needs of network operators as well, who are asking for more flexible software-defined capabilities through open source software work. This approach allows us to also engage with other stakeholders like cloud and enterprise companies who haven't previously been involved in the cellular market, but now in the 5G market, it's now considered this technology key to their operation as well. So Arm-based technology is the leading choice for building 5G infrastructure. Take off the cover of almost any base station, we actually could find there's a good chance you'll find there's Arm inside. We also believe that Arm ecosystem will be driving force for innovation in the cloudified era. Arm delivers best-in-class compute performance, best-in-class performance per watt, and best-in-class performance per dollar. As a result, technology from our partner can be found across network, powering everything from compute-intensive assets like centralized unit, CU, and radios to energy-efficient small cell unit, providing connection to remote assets. This experience has also allowed our partner to cultivate the expertise for integrating 5G's radio layer with the coming cloudified hardware and software. So this slide basically shows some of the silicon choice in the 5G ecosystem based on ARM. In order to accelerate innovations like those solution and user case that we just talked about, we announced the ARM 5G Solution Lab in October 2021 with the goal of fostering collaborations and innovations. We are partnering with leading telco systems integrator to host the lab, who brings a wealth of expertise in the segments with broad operator relationships and a proven track record running industry certified lab. The lab will provide all the key building blocks, securing remote access to state-of-the-art equipment, end-to-end components from UEs to radios, ARM's ecosystem, hardware, software, etc., lowering the barrier to work together. Across the spectrum, our partner can work on the end-to-end solution in integration, validation of POCs, and benchmarking activities for networking loads. Working closely with those operators will be enabling those blueprints for user cases that would get solution closer to deployment readiness. ARM's vision with Neoverse is about more than just a process IP. It is about delivering a complete infrastructure platform and the element required to enable a robust ecosystem of software, SoCs, systems, and tools for compelling new solutions from the cloud data center to the 5G edge. To further ARM adoption in the infrastructure market, we have been very active in open source communities and various organizations that support the open source projects. We and also our partners are deeply involved in helping further ARM ecosystem support in the cloud data center. Today, we are involved in over 100 open source projects and 25 standards organizations. This work spans operating systems, languages, libraries, tools, virtualization technologies, and workloads heavily focused on the cloud native application space. As we focus on the emergence of new cloud native workloads, being an active member of the cloud native community is also very important. We also see that developers are rapidly adopting cloud native software. We have a significant footprint of the OSS projects. Independent software vendors are already supporting ARM 64-bit architecture. The number of containers images written for ARM is over 100,000 on Docker Hub. And we have over 1 million CI/CD build work stream every month occurring on ARM hardware across a wide array of applications to perform software validations. We are continuously working with partners in the software ecosystem to optimize their application to take advantage of all the performance ARM processor can offer. At ARM, we are working almost every day to ensure that software can easily be being developed and deployed on ARM platforms. We see a future where all of the world share the digital data with, at some point in its lifetime, being processed on ARM. To execute this vision requires significant investment in software and support for developers who write the code. So here's some number I would like to share. Around 40% of ARM engineers support software development in some way. And we also calculate over 10 million developers hours invested by ARM in the first decade of our ARM v8 architecture, which is pretty much past 12 years. As we have recently announced our new ARM v9 architecture, we expect to expand, we also expect to these investment in the software to expand even further, helping to ensure that all the software just works on ARM, right? So this concludes my presentation today, and thanks again for this opportunity to allow me share my thoughts with all of you. Thank you.
Hey, thank you, Frank.
Thank you.
It's truly amazing. You know, all you and your team at ARM, your work. I think it's easier to talk about who is not using the Neoverse and Graviton, right? It would be easier and faster to talk about that list than those who are. You know, you talk about even supercomputer related customers in Japan and now Korea. That's truly impressive. I think you are perhaps in the best position to address this topic. You spend many years in technology leadership here in the U.S. as well as in China. So of course there are a lot of things, that's a lot of synergies between the two, but also there are a lot of differences. What do you see, especially in the cloud infrastructure environment, the hyperscalers in China versus the hyperscalers in US? What do you see are the major differences in their approach, and maybe the pros and cons? Can you share a little bit of what you have seen in both places?
Sure, definitely. So the business unit I'm responsible in ARM is infrastructure line of business, which covers hyperscaler, cloud data center, and 5G networks. And we launched our Neoverse platform in 2018, which is a dedicated roadmap, IP roadmap, and a platform for the hyperscalers or infrastructure product. And after that, actually, we do see very strong momentum for the product or the SoCs chips based on Neoverse, which I just shared in my slides, right? We see AWS, and we see actually AWS launched their own customized server CPU based on Neoverse. And for example, Oracle Cloud Infrastructure is utilizing the Ampere server CPU, which is also based on ARM Neoverse. Microsoft Azure also announced a similar plan, right? So we see actually in the US, or we basically refer to rest of world compared to China market. In the rest of the world, we see hyperscaler actually leading the way to utilize the heterogeneous basically computing, right? Basically in their cloud service, they are able to provide a x86 based cloud instance, ARM based cloud instance. And similarly, actually, we also see the same trend in China market, hyperscale China market. Maybe with several months, half a year or 1 year lagging behind, but we do see the similar trend in China market. And I just shared in my slides, Alibaba announced their first ever custom server CPU, which is based on ARM architecture, right? Very similar to the strategy AWS is marching toward. And we see Tencent and also ByteDance announced their intention to adopt the Ampere ARM-based server in their cloud service as well. So in summary, we see that very similar trend, but definitely there's some time lagging behind, but we are very confident actually our Neoverse will be successful in those hyperscaler market.
Great. Well, congrats. We look forward to hear more from you and as well as other speakers in our panel discussion.
Thank you.
Thanks again, Frank. Okay, so our next speaker is Michael Chen. Michael is the Vice President and General Manager of Advantest Cloud Solutions, or ACS, which is a strategic business unit within Advantest Corporation directed at helping customers accomplish intelligent data-driven workflows. Michael has 25 years of diverse experience leading product innovations and business growth across AI, machine learning, cloud data center, and semiconductor spaces. Before joining Advantest, Michael was the general manager of AI solutions business at Supermicro Computer. Prior to that, he was the co-founder of a deep learning startup. He has also held multiple leadership roles at several IC companies, including LSI, Marvell, and Vitesse. Michael holds an MBA from UC Berkeley, a bachelor's degree in electronics and communication engineering from the National Jiao Tong University, and has completed the executive leadership program from Stanford's Graduate School of Business. The title of his presentation today is "The Road to Chiplets is Paved with Data." So ladies and gentlemen, please help us to give a warm welcome to Michael.
Yeah, thanks, William. I'm sharing my screen. Can you guys see that?
Yes, very well.
All right, hey, thanks, William, and for your the introduction. And it's my pleasure and also my honor today to be able to share my views on the semiconductors testing in the era of the chip convergence. Just like William mentions there, right? I think, and also many of the speakers, including the Dr. Wu and also Frank just mentioned there that the semiconductor, just like many industry, is experiencing a data revolution. With more and more functions are carried on a chip, and the technology is more and more complex. Semiconductor manufacturers are packing more chiplet in a package. This product enables us to cram huge amount of components into a growing array of products, and all those components must be tested, and the corresponding amount of the test data will meet any reasonable definition of big data. So in this presentation today, I'll talk about that how industry leaders are actually leveraging the AI machine learning to do the gold mining on the semiconductor manufacturing, the big data, and how can they use that to deliver significant improvement in production yield, quality, and cost savings. I also talk about providing specific example of machine learning analytics solutions developed to solve the real industry problem. And also in the end, I also talk about that the Advantest is actually working with the industry to promote the open solution ecosystem to build the right data infrastructure and the application to enable the collaborations. So want to give a little bit background on the Advantest. So Advantest is a global leader basically in the AT space. The company has lead the way in developing new and innovative test solutions for the global electronics industry. The company is in the field in this automated test equipment for this with more than 40,000 systems installed worldwide. Those equipment are used in the semiconductor engineering and manufacturing environment to verify a silicon performs to its specification and make sure that it actually works in its end user application, which might be the consumer electronics, telecommunications, automobiles, medical instrument, cell phone computing, digital TV, to name a few. So the Advantest Cloud Solution is a newly formed business unit within Advantest with the charter focusing on provide the advanced insight for silicon manufacturing, testing, and system maintenance. So basically that the company has more than 5,000 employees from the more than 50 countries. And so the next one I want to give everybody some quick updates is talking about the little bit the trend on the semiconductor industry. So we've almost gone through the COVID-19 pandemic, and when we look ahead in the future actually looks pretty bright, almost blinding bright. Some of us, you know, that it took more than 40 years to get to the 200 billion revenue in the semiconductor markets. And then that double actually in 20 years. Now we see that the possibility of doubling again in a short of 10 years. After the mainframe days that put semiconductor on the map, we've now had the internet wave, which continues, using the silicons for networking, for computing, for AI, and then mobility, waves comes in, such as the smartphone, self-driving cars, and coming the virtual reality, the meta universe. But now we have this wave, someone called it the age of convergence, which is driven by AI that creates these virtuous compounding cycles of data. And it's not like these waves are coming and going. They are in phase, and they're going to produce this growth curve. So from the unmanned driving to virtual reality, from the artificial intelligence to cloud computing, from 5G to the IoT, many driving forces jointly promote the continuous advancement of the semiconductor manufacturing and the testing technology. With a huge demand of the electronics ever complexity, and in the face of the bending the curve of a Moore's law, semiconductor manufacturers are moving to a chiplet-based paradigm, as many of our speakers, was talking about using the chiplet to enable more complicated, SoC and the silicon development. And this part enables us to cram huge number of components into a growing array of products. So the traditional methods, right? I think for the traditional the manufacturing and the testing process are less and less suitable, and also becoming cost prohibitive to managing those data explosion. Let's take a look at the semiconductor test ecosystem. Huge amount of the data are generated and collected across the different stages of the manufacturing life cycle. Right? I mean, you can see the chart here from the post-silicon validation, wafer acceptance testing, wafer sort, all the way to the system level test in the right. Semiconductor manufacturers they struggle to realize the value from the data they collect. Some of the key challenges that the vendors that they face today, including, for example, how to integrate all the data sources across the entire IC manufacturing supply chain, how to combine advanced analytics and the machine learning capabilities and enable real-time automated production control. So semiconductor test value chain it's a pretty complex and actually outgrown, from the point solutions lots of the the manufacturers and the vendors are using today. Over the past 20-30 years, right, we've been spending most of the time optimizing the testing efficiency at each insertion point. But now with the AI, high bandwidth networking, cost-effective storage, and advanced computing capacity, the industry has actually what it takes to do the gold mining on semiconductor data. But that's not enough. Actually, we also need infrastructure and a partnership in place to enable the supply chain to realize and extract the tremendous value from the big data. So the question here actually is that how do we do that, right? I think if we look at this today, right, the industry actually has done a pretty good job optimizing efficiency. But actually, what we're seeing is that, because of the fragmented and distributed nature of our industry, a lot of those solutions were self-developed, isolated, and generally unscalable. The industry actually did a wonderful job, in the time, right? But some of those solutions that develop are quickly become obsolete, especially with the modern data centers and all the capabilities available. The more data actually is shared forward and backward, and up and down in the test ecosystem, the more valuable it can be. So we at Advantest actually has a responsibility to the industry, as it is our system that service most of the individual test segments and insertions today. So the industry actually, in our, a lot of this, our experience working with a lot of the industry today, what we find out is that the industry, lots of these, the semiconductor manufacturer, they were able to do, what we so-called is a little data. For example, optimizing a specific test insertion, doing analytics like optimizing the yield for wafer sort, stuff like that. However, the billion question, right, it becomes that with the availability of the AI, right, and the computing and the processing, as well as the advanced algorithm, what can the semiconductor industry do with the big data? And that's actually the question we are answering, with a lot of our customer and the supply chain partners. Well, I'll walk through 3 use cases in the next couple slides there, and talk about those, easily add up to more than $1 billion impact to the overall manufacturing and the testing efficiency. And basically that just a heads up, those 3 use cases are just one of the 1,000 use cases actually, that we are working with many of our the customers and ecosystem partners, and there are more to come. And also just want to note here, those savings are just calculated based on from the yield and cost saving perspective. There are actually a lot more factors that push value much higher. And also the $1 billion savings are actually we are calculated based on today's dollars and the volume we see. The impact actually will grow as the industry grows. So the first use cases I like to share with everyone is that talking about how do we optimize the entire test supply chain. As a previous stated there, we've been doing pretty good at optimizing the individual insertions, and often see those insertions are managed independently and are also, geographically in different parts of the world, right? For example, different OSATs, foundry, and also the fabless, they are located in different parts of the world. But what if we can look at that, all those, the supply chain holistically, and apply AI and the machine learning to semiconductor big data across different stages there? We could have actually, fully connected and using the integrated workflow, where machine learning can help us to rebalance our test budget to maximize the entire value, rather than just focusing on insertion-specific optimization. Machine learning can actually dynamically adjust the testing limits at each of the insertion to maximize that value. So in this particular case here, you can see that the machine learning is making a recommendation to fail some die earlier and fail some package chip earlier. And as everybody knows that the cost of those script, right? I think in the early stage, right? I think in the die or the wafer form, it's actually a lot cheaper in the later stage where you package into a package, or even in the final test or the system level test stage, right? So they actually give a overall cost saving from the both the manufacturing efficiency perspective. So in a nutshell, right, if you look at this case here, machine learning, right, can determine that the die or package will likely fail later in the process, then fail it not, right, and fail earlier. I think that's the one of the key points. And actually the opposite is also true. If the machine learning can determine that it's actually likely to pass, then skip it to the front of the line. And actually both can providing the net positive outcomes from the manufacturing efficiency and overall cost saving perspective. And in this particular example here, we are assuming 1% in the system level test improvement. In the table, we are using making assumption this is 10 million units per month for the cell phone, the mobile processors here. So the second the use cases here I want to share is actually an example. Want to talk about that how can we actually leveraging the machine learning and to helping on the to sort the die or devices or the wafers into different groups and then determine the complex relationship much more easily and quickly than actually a team of the the engineers, right, the experts that in the semiconductor manufacturers they can do. So in this particular case, the machine learning is being used to examine the data and recommend various level of performance as well as the risks, where the manufacturer they can use to their advantage. By doing so, the silicon can actually be sorted right and sold to the right application for the right market, which improve the margins and improve the quality as well. As actually, I mean, as of today, our industry is doing some of this right to a certain degree, but with the fully connected system and the feeding the data forward and the backwards throughout the semiconductor supply chain to where it needed, we can actually accomplish the die sorting right a lot more efficiently. So I think in this particular case, we're working with some of our the ecosystem partners and the customers out there. We are seeing that the benefit is that instead of taking weeks or days to accomplish the same thing, right? I think usually we can through those the integrated workflow, we can get those done with a matter of hours. So in this particular use cases here, right, we are talking about just to highlight the one aspect of the value, right? That is being able to sell the failed devices into I mean, we can call it the tier 2 or some of the tier 3 market segments. The next, but not the least, the use cases I want to share with Tim is actually one of the holy grails of the in the industry, right? And specifically that how can we leverage the AI machine learning techniques to determine the possible root cause for failures in real time, and also how do we make some recommendation, right, to fix some of the those issues identified. And the value actually of this particular use cases is pretty high because of the high cost of delivering low quality, to a customer. I mean, for example, I mean, no one want to see that their product fail on arrival, right, and having troubles. I mean, this is actually going to be detrimental, not just to the brand but also to the company image. So manufacturers often, when they see issues right in their silicon, typically, it could easily take weeks, if not months, try to determine the root cause, right? I mean, whether that's in the design phase or in certain manufacturing or the test cycles, right? So imagine that with this fully connected workflow we show in the slide here, right? I think using the AI and the machine learning, we can correlate the possible failure mechanism across the the manufacturing and the test life cycle. and providing this, the resolution. A good analogy actually is that you can think about how we do this is that just like everybody, I mean, using your GPS on your car, right? I think when the GPS sees there's a traffic or there's a traffic coming, it would automatically reroute you to the better routes. And the financial market actually is using some AI techniques, right? I mean, try to do the risk mitigation in there as a part of the risk, mitigation strategy. So from the semiconductor testing perspective, the machine learning determine whether there's gonna be a system level test failure, and they recommend a series of additional tests at the wafer sort or at the final test, and screen the defect parts earlier in the early stage. And because everything is connected across this, the test supply chain, the system can actually implement the changes automatically live and issue a report to optimize the test flow and significantly reduce the manufacturing cost. So we've seen some of the some good examples, right? I mean, which is showing a huge values, right? I think to improve the manufacturing efficiency and improving the overall the test cost, right? So what can we do from here, right? I think the important things is that today, right? I mean, we are seeing that there's lots of the isolated optimization at the each insertion point, and with a lot of this point solution, right? I think the important things is that how can we enable the fully connected system, right? Vertically and horizontally across the silicon manufacturing life cycle. In the next couple of slides, I'll talk about how can we actually get this done and what is needed, right? I think so. The step one is that we have to get to the vertical integration in place, right? So when we talk about the vertical integration, there are thousands of the systems servicing the industry. But from the test cell, the management perspective, right? I think that you are talking about there's lots of the data, right? Including that the semiconductor fabrication process can collect, right, from the tester, from the handler, and there's a lot of sensor from the equipment, from the environment, as well as some the data from the low boards socket, right? So all those data has to be vertically integrated, and we need the ability also need to be able to process the data and being able to make some decision at the edge. So so how do we do that, right? I think the solutions that the Advantest, the cloud solution recently introduced, we call it ACSH. It's actually a high performance computer solution with the capability to deliver machine learning and analytics capability, enable the real-time adaptive capability during the production kind of process. The ACSH enable true adaptive test, allowing the real-time adjustment to the production flow and limits, and with the different use cases available from the open solution ecosystem partners. We are seeing that the ACSH actually is helping the semiconductor manufacturers to improve the yield, quality, and reducing cost. We are in the process deploying these production-based ACSH systems, today as we speak, and we also in the process to enable many of the use cases like what we described previously. So the next page here, just briefly talking about the ACSH. I'm not going to go through too much of the details here, but pretty much here we are talking about ACSH is a real-time secure cloud-connected testing cell compute solution enable high-performance compute for rapid test decision making, which is allow the true real-time adaptive test flows, enable the phase secure connectivity between those testing equipments, and improving the OEE, and providing those scalable and portable application deployment through the containers. So we talk about how to do this from the vertical integration. From the horizontal perspective, right? That's actually the step 2, and actually also a very important step, right, to achieve the vision where we talk about how do we connect the data streams, right? Both the forward and the backward across the test and the manufacturing value supply chain. So the horizontal here we talk about specifically is that how do we connecting those data from design, right? From the design house, the fabrics, right, to the fab, to the all the the manufacturing, the offsets, and where there's lots of the manufacturing and the test insertion, and a lot of this infrastructure already today, and how can we go through using this partnership and connect the building the right infrastructure to connect the ecosystem and the supply chain together. So what's pretty interesting here is that we can feed forward of the design, test, and the parametric and the performance data, right? And we can also do this all the way into the front end of the fabs and even into the chip design. For example, feed forward of the parametric test, diagnostic, and in-field data, and with all those, we can identify actionable insights through the silicon life cycle and deliver better yield improvement and reducing the root cause for the wafer yield loss, and also the equipment downtime. And many times we also see that with those integrated data we collected and with the advanced analytics capability, we are seeing that it's not just also improving the yield, but also improving the capacity and efficiency from the OEE perspective. So at the summary here, I want to share that the advanced cloud solutions, our vision is to realize this fully connected ecosystem. It is important that we are building a open solution kind of ecosystem. We are working with the partners like a Portentix, PDF solutions, as well as Synopsys and many other ecosystem partners, and building the solutions and applications running on top of the data. And as you can see in these slides here, right, on top of the in the bottom, all those through all those different stages of the semiconductor testing and the manufacturing equipment, the ACS is building the so-called data superhighway, right? And from the data superhighway, we are collecting those real-time data and providing those the data the database, and enable the data warehousing and make it available for not just the customer, but also the third-party ecosystem partners to be able to continue to innovate, right? And providing those different analytic solution and applying a lot of those machine learning algorithm to be able to analyze those big data. So in the end, that it is our vision that we are providing that environment enable the customers and the manufacturer can innovate together and being able to solve a lot more nowadays there's a shortage problem by having the yield and the manufacturing efficiency. So with that, I would like to conclude my presentations. So if there's any questions, feel free to ask. Yeah.
Well, thank you, Michael. That was amazing. I mean, from a traditional wafer probe, final test, to this, what your group is doing, so a lot of that is about bringing data science into this fairly, traditional technology area. That's just, very, very inspiring. And you talk about the ecosystem. As you and I chatted a couple of weeks ago, my company is really a startup called Proteontex. We are hopefully we can work together, right? I mean, we put those agents during the design stage to provide visibility, so that we can detect degradations before degradations turn to expensive failures. With a little bit of time we have, do you have other, examples that, you mentioned the PDF and a couple others. Do you have other, partnership examples you can inspire us, as part of your ecosystem?
Yeah, absolutely. I think, other than the Proteontex, PDF, we are working with many ecosystem partners like the Synopsys, and then there are many more partners that actually we cannot be announced, in the pipeline. I think the key point here is that I think everybody knows that the AI machine learning are fairly popular in the other vertical industry like healthcare, financial, many other industries. I think in the semiconductor, manufacturing, especially from the testing perspective, we feels like we have a lot of opportunity that together, right? I think with the right application and with the right infrastructure, right, we can build that the data infrastructure, and based on that, I think the important thing is that with this the open solution ecosystem, right, Advantage from the testing infrastructure perspective is able to provide those data infrastructure and enable a lot more innovation, and work with those partners. So I think the beauty is that moving forward, right, I think our vision is similar to like Apple, right? Apple is providing a leading smartphone hardware, and also enable the ecosystem, the partner developing the application, right, to continue to provide the cost saving, the yield improvement, as well as the overall efficiency. I think that's the vision that we are definitely excited, and we move forward to work with the industry to make this vision happen. Yeah.
Great. So your group is the Apple and iPhone of the test equipment business. Very good.
Yeah.
Okay, so we are a little bit behind our schedule, but this is probably a good time to thank you again, Michael. But please, as we all know, the even more exciting portion of the program is coming up, the panel discussion. So Alex, maybe, but before I pass the baton to my colleague Richard here, can we show the prize drawing? The most one of the exciting part of CASPA, a typical CASPA event. So Alex, can you show the QR code for people to participate in the prize drawing that will take place at the end of today's program?
It's going. Oh, can you see it?
Not yet. At least I cannot. I don't know about other people.
We are still seeing the advantages.
Yeah.
Like,
Oh,
We can see it. There's a bit of delay.
okay, seeing it now.
Are you seeing it? Can you see it?
Yeah, my cell phone sees it, but the computer didn't.
It said showing it.
Okay.
There we go.
Got it.
Thank you. Yeah, so, feel free to, scan the QR code, and then we will have the prize drawing toward the end. At this point, I'd like to invite my colleague, Richard Yan, to host the panel discussion portion of today's event. Dr. Richard Yan is currently the CTO of Fortune Precision Equipment Corporation, responsible for central R&D and product engineering in semiconductor equipment components. Prior to Fortune, Richard was a senior director at Intel. His team has won numerous honors, including Intel China Award and Intel Achievement Award. Prior to that, Richard was senior engineering manager at Lam Research and group leader at Applied Materials. Richard has been working through the ecosystem of semiconductor manufacturing supply chains from fab, process equipment, to components. Richard received Bachelor of Engineering from Zhejiang University and PhD from University of California, San Diego, in material science and engineering. He is a lifetime member of CASPA and has served as executive director of Symposium. So without further ado, ladies and gentlemen, please help me to welcome Richard Yan.
Thank you, Waylon. Thank you, Waylon, for the warm introduction. And also thank you, Ian and the Symposium team organized a wonderful event. And we held I just noticed we took a brief note about the speaker. We cover the ecosystem all the way from the materials, fab equipment, and also we have good representations of IC design, all the way to the final electronics and systems. So I think in the next 40 minutes, probably we can only spare 40 minutes in our panel discussion. So I would like to get our speakers warm up again, and then also other audience, please stay through. The time is pretty precious. So we like to organize into 3 sessions. The first one, we'll go through the roundtable introduction about the speakers again, and then talk about what is the Mac trend each of the speakers has seen in their segments of the ecosystem. And then the second session, we spend time on a few focus topics that we have gathered. And then the last and not least, we'll save time to take a few questions from the audience. I could see that the active participation in the chat room. I would like you to remain in the panel discussion and like to hear from the speakers on the question that you have raised. So let's see here. All the speakers, could you turn on your voice and video? Can you hear me?
Yes.
All right, great, Rob. We have Rob. Do we have Ted back? Ted, is Ted
I'm here.
still?
I'm here. Yeah.
Okay, great. And then we have Hui Min.
Yes.
All right. Frank. Frank, are you on? Okay. Yeah. Well, let's Alex. Please try to pin Frank if it's not there. So I'm going through a bit introduction about stuff for myself. So I have been working in the segment of fab manufacturing equipment, and currently my role is in the components and at components level and materials level. So before my previous work, I had been working at the applied materials in the equipment, on the deposition equipment, and then at Lam Research working on the etch equipment. When I joined the Intel, working on 3D NAND process development. So the trend that I have seen overall is in my last the 20 years in the semiconductor industries, that I have seen very clear trend is and I have personal experience is the process node has evolving from planar to 3D. The first evolution was the flash NAND process, starting from 2012. We see the first production of the 24 layers of the 3D NAND, and I was personally involved in the process tool development, and has been a great transition. And we see many new market leaders in this segment emerged, and also it dramatically reduced the cost per bit for our storage. So that's what's one of trend. And the second segment I've seen in for the logic, so I was involved in the gate-all-around selective etch tool design for gate-all-around in 2015, and had brief, I think overlap is the Huimin's team in Albany, and I was as Albany as Huimin projected the vertical, the integration, the gate-all-around, as IBM has demonstrated, is the second trend we have seen. And I would say that DRAM, DRAM is probably the third major chip technology, or if start from I mean, they will start from the same trajectory from 2D to 3D NAND. Again, it's a great opportunity for the folks in this ecosystem, right, to have technology innovation and take the lead in the technology innovation, and that's opportunity for the new market leader to emerge. That's the first trend I have seen from perspective of process equipment. And then second one is more recent. We see that chips shortage. That's from, and then you see everything shortage, including we have the fab capacity shortage. We have the equipment shortage, and now we see more there's component shortage. You can have the billions of orders piled up. It's all held up because of the components. We don't have the generators. We don't have the special parts, and that's what I see as more on the business trend. And there's more consolidations in the components that's evolving. The less of the consolidation in the chip manufacturers, you start to see more very active the business consolidations in the components and materials segments. And this is also an opportunity that put our Silicon Valley spirit into work, that we could have technology innovations combined with the new capital investments. Maybe that's an active component, the development. And that's why I personally jumped in this swim lane as a CTO in Fortune. So that's the two trend I have seen. And then I would like to next one is introduce Ted Spear. Ted has been in this industry more than 20 years, more than I have seen. And Ted, from your speech, I think you have been very active advocate for RISC-V, but your experience is more than that. Would you speak a bit about your experience, and what do you see as a trend in the segments that you have been working on?
Yeah, thanks. First of all, amazing lineup of talks you had today. Congratulations to the organizers. Really enjoyed listening to all of them. So good job there. Don't know how to address all your questions exactly. Yeah, so I've been involved in FPGAs since 20 years. 1987 is when I joined Actel at the time. So I've been at the same place, but always moving, I would say. So we're not the #1 supplier of FPGAs, but doesn't mean I don't want to become the #1 supplier of FPGAs. So we're always looking for ways to be disruptive. And so I was kind of primed to jump on RISC-V as soon as I saw it, and take the opportunity, and definitely feel like that's definitely going well, and has exceeded everyone's expectations. And but I still there's definitely still work to be done, and part of the opportunity today definitely is to make appeals for people to continue to support RISC-V and help us with our effort, because I really do feel like with trends I cited there, that RISC-V has a significant role to play, and is already playing a significant role in solving the next generation compute problems. So, and then we're definitely, as a FPGA organization, we're walking the walk. We used RISC-V, and what it really did for us was gave us the opportunity to innovate, so we could work with a supplier and make changes to the microarchitecture as needed to meet certain needs of our customers. The area of in this case was reliability. But you're going to see an ecosystem of RISC-V suppliers, and so if you're building a system today, you're going to want some customization, and you're not limited to one supplier. There's many suppliers, strong suppliers today that can help you solve your own problems with RISC-V. I'm not sure I answered your question exactly.
All right, yeah. We like you to share what you see as the back trend in the field that you have been working on for over 2 decades.
Just say that again.
Yeah, you have speak to the question that I had. Thank you,
Okay.
Ted. Yeah. All right. Okay, so our next the panelist is Rob Main. Rob has been today has been a great advocate for open source. Ted, would you like to Rob? Could you speak to introduce a little bit of your background again, and speak to what is the Mac trend that you have seen in the segments that you have been working on?
Sure, happy to. And congratulations again on the excellent seminar this afternoon. I truly enjoyed the breadth and depth of the papers or talks that were given. So very, very enjoyable. So I've been fortunate in my career that I've gotten to work on a lot of different challenging problems with many talented people. I've worked in the area of design for test, built-in self-test, static timing analysis, optimization, transistor level analysis, to name a few. And those have all been done in conjunction, and that's primarily all in EDA development, but also hardware design early in my career in terms of built-in self-test. But that's all been in conjunction with chip design teams. So as a result of that experience, initially at IBM, but then extending into Sun Microsystems and Oracle, it gave me an opportunity to work very closely both with software developers in EDA, but also with chip design teams closely to be able to understand their problems up front and then be able to implement algorithms to help solve their problems in a timely fashion. And certainly Magma gave me an opportunity to have a startup experience as part of my career and to understand the challenges in developing solutions very quickly for customers who were waiting for those to help build the company. So that was all a great experience. Open source is a unique opportunity, I think, to help build a collaborative ecosystem, similar to what originally, like I used to see at IBM, except for it was all within one company. I know from my experience back then, and maybe it's still true, I don't know, but there was always a person at IBM you could contact at another site or an IBM research who would know the answer to the question. And that was a tremendous resource, as I fondly recall. I think open source allows for an opportunity for collaboration amongst individuals from different backgrounds or different companies or different universities to be able to participate together to solve complex problems. And I think that's going to help break down barriers and help faster innovation as we go forward. It's going to take time, though, for that to occur, because as I mentioned in my chat, there obviously are different barriers to entry for that. And some of those barriers are needed, of course, as we saw earlier in the talk by Huiming of the research that's ongoing at IBM at Albany, right? That takes tremendous amount of talent, tremendous amount of resource in terms of both financial or capital investment, if you will. And then also to build the EDA ecosystem around that to design enablement. That takes a lot of money and talent too, right? But I hope that we can, over time, enable that to be more collaborative in nature for a broader community. So we'll see how this goes. It's going to take time. It took time in software. So, but I am optimistic that it will occur.
Thank you, Rob. Thank you, Rob. Next one, I'd like to bring Huiming back to give a brief introduction and what you see as the Mac trend in your segment.
Thanks, Richard. By the way, thanks to CASPA for inviting me to be with this audience and also with my fellow speakers. It has been a wonderful experience to hear the talks and have some interaction here. Richard, one thing I do want to echo is what you have said on that 3D component. Yes, I see that started with NAND. I see that starting to be there in logic, and I see the DRAM is also following. So that's actually a very good trend. I call it the Z direction, the vertical direction. We haven't used a lot in the past. Now we are exploring that direction, which is not constrained by so-called lateral scaling component of it. The second one I indicated, but I want to share a little more on this, is chip and the chip technology. Essentially, what we see here is in the next 5 to 10 years before the next lithography, I mean, intrinsic transistor scaling has been driven by lithography, as we all know. Before the next breakthrough in the patterning lithography capability, I would say chiplet likely is going to play more and more important role. Very likely in the next 5 to 10 years, chip and the chiplet technology are going to be equally important when it comes to semiconductor logic chips. The third one, let me add to this conversation. I mentioned this National Semiconductor Technology Center. Essentially, it's an initiative. The US wants to revive semiconductor manufacturing and research leadership in the US. One thing I've learned, actually really triggered by my ex-IBM colleague, Rob, when he talked about this open software ecosystem. Essentially, this NSTC, to a large extent, it's more or less an open hardware innovation platform for semiconductor industry. Maybe I'm going to talk to Bob offline to learn a little bit from his past experience. How do we do this together for semiconductor technology and semiconductor design from an open innovation platform perspective? That's the one thing I want to add to share here with this audience and with Rob as well.
Thank you, Huiming. Do we have Frank back? Frank, could you speak to a bit your the introduction?
Frank previously communicated with us that he's not able to make the panel. It's Michael who is able to. Thank you.
All right, great. Hey, Michael, yeah, we'd like to bring you back. You just spoke passionately about the testing, but I think you're more than that, your experience. Could you tell a bit your background and what do you see as Mac trend in the segment that you have served?
Yeah, sure. Well, first of all, I'd like to congratulate the CASPA, the key members, and also everyone. I feel like this is a very inspirational kind of event. I learned actually a lot from both the depth and also the breadth perspective. Actually, this is a very good events for me to learn a lot of the insight from the different aspects of the semiconductor industry. So want to briefly talking about that. Well, myself, I think it's I recently actually just joined this Advantest, and and I'm running the Advantest cloud solution business. With my background, actually, I was before the Advantest, I was actually, working with quite a few top semiconductor company, helping them to implement those AI machine learning infrastructure. And also before that, I was a co-founder for a startup company, focusing on, building those, machine learning, deep learning, infrastructure for the some of these top leading cloud solution provider. And also before that, I was having this taking the leadership role in a couple semiconductors leaders like Marvell, LSI Logic today becoming Broadcom, and the test semiconductors. So talking about some of the views from the semiconductor industry, I think again I think I like to continue some of the the experience and also the sharing my view on how can we continue to leverage the AI and the machine learning into helping on the semiconductor manufacturing. Right, I think. In many of the my experience, actually, or actually I can say the ongoing experience with the semiconductor manufacturer, right? We are seeing that I'll give you some examples. Like for example, just like Dr. Bu mentioned, there is that with this heterogeneous computing, right? I mean, we are seeing that this MCM, right, the multi-chip module package kind of a silicon is becoming more popular. And then what we're seeing is that there's a growing demand for those, the silicon, manufacturer. They want to make sure that the yield, right, is getting, improved. And specifically talk about within a MCM kind of a package, right? We are talking about 10, 20, sometimes more than 50 chiplets, right? And it's not a good idea to see that in the semiconductor final test or the system level test, seeing some MCM packaged silicon fail, right? I think it's a very costly kind of a situation, because you are not just, it could be just one chiplet inside let's say a 50 chiplet fail, right? But you are actually losing the opportunity selling those silicon, right? And it's both a loss from the manufacturing cost, but also a losing on the business opportunity, right? So this is where that we are seeing a growing and also a strong demand starting to apply data analytics throughout those various manufacturing test stages, right? And specifically is that we talk about the connecting, the data source across the semiconductor supply chain, right? And being able to correlate the data, from the upstream data to the downstream, and being able to find out the source of the problem earlier in the manufacturing cycle. I think this type of the capability, being able to, number one, access the data from different stages of manufacturing, and then number two, being able to provide that capability, right? So the semiconductor, manufacturer, they are able to, using those data to feed forward or feed backward those data, and being able to analyze, hey, what will be those potential root cause, right, for that, failed silicon, right? And then, and at what stage, right, out of those, the 20, 30 chiplets, right? I think package there, right? How do I make sure that from different source, right? I mean, how do I guarantee the total traceability of those data? How can I make sure that I can, using those, machine learning, and being able to continue to monitor the quality, and being able to provide some insight, right? I mean, to improve those. I think those are the area we are seeing that it's a trend. It's growing, and it's starting to, not just a theory. Actually, we are seeing many of the top manufacturers are using that technique today.
Yeah. Hey, thank you, Michael. Yeah, get into the folks topic. In the next 15 minutes, we select a few topics we'd like to have the discussion. So the first one is Michael has just speak a little bit is chiplet technology. Now the question is will the chip technology overpace chiplet technology overpace the chip technology in delivering the system level performance? We looking at 5 years from now. And then this question is first one is for Huimin.
Hey, thanks, Richard, for throwing that question at me. Well, I do have a research team working on both technology fronts. In fact, I do have most of the team actually today still work on chip technology, a relatively small but a growing size of the team, significant growing size of the team on the chiplet technology. When I look at there are two components here. One is, will chip technology and continue to move forward? My answer is definitely yes. Will the return of that investment start to flatten out? The answer is also yes. Then you look at the return of that investment in the chiplet technology space, especially in the next 5 to 10 years, will it outpace from a $1 average perspective in terms of return? My assessment is soon that two curves will cross. But it depends on the speed of that or the pace of that cross point will depend on the application. Likely that cross point will be lower in terms of the entry level for low power and mobile application. It will get a little bit higher bar when it comes to AI and high performance application, but eventually it will all catch up. The second component I want to add here is more like, when I look at these technologies, we need work like a human being with two legs, chip and a chiplet. The reason I say that, if you look at the nature of how we integrate these things, I would say they are very much complementary. And we need the strengths, we need the advancement in both technologies to move forward. One beautiful thing about heterogeneous integration is not just it's about a technology. It's actually, if you think about it, it's a key enabler. Eventually, I think in the next 5 to 10 years, likely, it can enable a heterogeneous computing architecture, very different than today's von Neumann computing architecture possible. So that's the direction that we are. I think our industry needs to be heading. That's how I call heterogeneous integration. It's an enabling technology. It enables the industry to build something very different than today. So let me just pause here.
Hey, thank you, Huimin. Yeah, it's very insightful in terms of speaking to this how it enabled the chip architecture, and also speaking of the cost perspective. I think in the end we judge by PPAC may be still relevant. So on the same topic, chiplet technology versus the chip technology, I also like to hear again from our panelists.
Yeah, so there was an announcement last week or something from Intel. So there, some people should be aware of. It's called UCIe. It's not just Intel, actually. It's a consortium. It's a chiplet technology based on CXL. So members of the consortium are pretty powerful. You got Intel, AMD, ARM, Samsung, TSMC. So we've already had meetings with them. So it sounds like, that it's always been, it's a little bit of a chicken and egg thing. To design your chip based on a chiplet, but here's there's definitely a new effort that's recently announced that people should be aware of. Our own use, my division, but other divisions of Microchip have been kicking the tires, and I know they always want to go 3D, so the Z direction is of interest as well for chiplets. So they see a lot of benefits for going 3D. It's much more difficult, I think, to imagine, or the 2D creates actually problems in architecting the overall system for those teams. So I think when you can stack two unlike chips on top of each other. I think that I don't think, not seeing that we're there yet, but that's definitely is a step that we have to head. But I can imagine we heard about the power underneath the chip. You're going to have to, when you start to have these 3D stacks of chips burning a lot of power, you're going to have to have heat exchangers also throughout the system to suck the power out of that stack. But it can save power in the end of the day, because the Z direction is much shorter distance for those electrons to travel than all the way across the chip to the next chip.
Thank you, Ted. Anyone else like to speak to the what do you see as a chiplet versus chip technology?
Yeah, this is Rob. So I agree with Wenming's comment relative to that. There's going to be advancement both in packaging technology, specifically chiplets, and also in process technology, and that also that there's likely to be more quick advances in the chiplet technology, just because semiconductor research and advancement is such a difficult and challenging problem, getting harder as they go along. I also agree that chiplets, by allowing for heterogeneous type of entities to be placed on a higher level package, is a real advantage for different developers in the market, because it allows you to pre-select IP from different providers and not have to wait for, say, like a physical macro to be proven in on a new process node by one of your favorite suppliers, or by your own R&D team that you can pull into it. So it really does allow for a much easier pick and choose, so to speak, mechanism for developing product. I think that's a huge advantage. And I also say that years back, these packaging solutions were generally comprised of homogeneous type chips. If you look at the IBM mainframe back in the late 70s, early 80s, it was all bipolar. They were TCMs, or thermal conductor modules, right? That was all the same underlying chip technology, and similar for MCMs too, by and large as well. So I think chiplets really does open up a new game field for all of us.
Yeah, thank you, Rob. Yeah, I think if we could, this one is really a Mac technology chance on the Z direction. I think personally, as process technology, we feel a lot more to play in the third dimension. I think probably the same for the IC designers and the end system lab designers. There's open up a new dimension and more new possibility. The next topic I'd like to start with Rob is that Rob has been advocating on this open source in terms of the software development. You have great experience, and now you call. Question is now, can the trust be built in open source hardware, IP, and tooling development?
That's a great question. So I suppose in some ways I've been known to ask hard questions, and so there, there's no secret that there are challenges or problems when you're building any tool or application, right? And then invariably it gets back down to the underlying silicon qualification and what type of test structures that were used for device characterization, for interconnect characterization, et cetera. What's your collaboration level with the foundry? Those are very important ingredients relative to the physical design tools, logical verification, or physical design verification, physical design tools and electrical verification tools. And then also, of course, the logical verification tools. I think greater progress has been made on the logical verification tools. I think it's on the physical design and associated electrical or physical verification tools in the open source community that is going to be the bigger challenge. There certainly is a lot of effort in that area. Some of that is being funded by the US government, as I mentioned in my slide deck. I think there's definitely opportunity to help improve this. Perhaps there can be some type of partnership or arrangements to be made with different EDA partners in this area, right? In terms of how that collaboration could look. But again, it is a challenge, of course, because there is a lot of money invested in this, a lot of R&D time. So we will see how this plays out.
Hey, thank you, Rob. I also ask Hui Min, the sort of NSTC that you have been championed. Will that help to enable more open collaborations in terms of the hardware, IP, development?
That is truly one of our intentions. I think, well, as the way that you have asked the question, there's still a lot of things need to be figured out, especially in the hardware space. Who owns the IP and what is the sustainable business model based on that IP ownership moving forward? These things we still have to figure out. The way that I see this NSTC first is going to be a public-private ecosystem, which we know how to do. Like today, the Auburn Facility Nanotech Center is based on IBM and also New York State NY creates co-owned system. They are the landlord, but we work together on technology development. The second component I do want to add here, which we didn't talk too much, but it's extremely important. Talking about technology innovation, I think in the US now, what we're facing here is really the talent pipeline when it comes to hardware technology. I think some of the speakers probably indicated that as well. I think under this NSTC, we have a very focused session to I would say, grow back that investment and collaboration between industry and universities. That's extremely important moving forward to build a sustainable model on this platform.
Hey, thank you, Huimin. I think last one, maybe I'll ask Michael, since you have built in ACS cloud-based test platform, you have access to a lot of end users results, probably also in the loop of verifying the designs. What do you see is how to, in part of this ecosystems, how to build the trust in terms of open source hardware development?
Yeah, so yeah, that's actually a really good question, right? So when we talk about the how to do the gold mining, right, for semiconductor test data, right, and the manufacturing data, right, I think one of the critical things, right, I think nowadays, right, a lot of people is asking me, say, hey, Michael, I think how come, I mean, we are seeing people are using AI machine learning in different verticals, healthcare, financial, in retail, in every aspect. I mean, many vertical industry. How come we are not seeing too much on the semiconductor, especially in the testing space, right? So one thing, what we're doing is that, is that the source of the data, right? Because there's a couple of things, right? There's a couple bottlenecks, right? And opportunity for us to make it happen, right? Number one is that first of all, the source of the data, as I mentioned, right? Horizontally, I mean, through the semiconductor manufacturing process, from the design, to the foundry, to the the offsets, right? I think across different stage, right, and the different vendor, and also in different geographical kind of location, right? So there's a privacy, there's a concern of people, how you share those data. There's a security issue, right? That's number one. And number two is that and also the infrastructure, right, to being able to collect the data from the different stage of the manufacturing, right? How do you collect those data from both equipment data, test data, and some of the metadata from different testing equipment? And how do you providing those the real-time, low latency type of information and being able to fit into the a repository of the data? I mean, how do we build it, right? And then the last but not least is that and once we build it, right, I mean, how do we providing a robust analytics kind of a platform, right? Enable the data scientist people, right? Either from the ecosystem partners or from our customers, or for the advantage of our internal development, right? I think those are the things that that's the things we are focusing on, right? I think so. Answer your question, how do we supporting more innovation, right? I mean, and encourage the ecosystem to participate, is that we are as we speak, right, we are building the so-called the data superhighway, right? So basically, given that the Advantest is the market leader in the semiconductor test industry, right? I think we have a big installation base for those testing equipment out there, right? So we are actually in the process, right, and to providing a lot of those the connectivity and also the edge compute capability. That's the infrastructure we are building for the data superhighway. In the same time, we are partnering with those ecosystem partners, right? Provides the standard, API interface, right? So they don't need to worry about, hey, at a different stage of the fabrication process, right? I have to deal with different, equipments. What is the right API, and how do I collect those data? And then, so they can, our partner, they can focus, right, on what they do the best, where they are developing those, the analytics solution, right? Providing those, those innovation on top of those standard, data, API, where they have access to those data warehouse, data lake kind of information, and they can just, process those, spend more time driving the insights instead of worry about getting the infrastructure, right? And worry about how to get those data. I think those are the things we are doing to help to, to improve the speed of innovation. Yeah.
Okay. All right. The one last topic for the panel discussion. I think it's about RISC-V. RISC-V, as Ted has said, he has been 16 times promoting it in the speech. Actually, CASPA, we have been hosting the RISC-V topic since 2016. I think at the time we invited Sci-Fi founders, CTOs as well spoke. So the first question will start with Ted. What is the challenge now you see that remaining challenge for the RISC-V to succeed? And what will be a killer app for RISC-V?
Yeah, I guess I asked myself tough questions as well. The success. So RISC-V it's a disruptive technology. It's not in the ISA necessarily, but in the business model. So we're a key pillar in opening up hardware development. But that it's a different business model. So when the x86 was coming along, you had the PC industry, Intel and Microsoft were making all the money, and they could afford to build out their ecosystem, completely on their own. ARM came along and definitely had a killer app, enabled the killer app, really with the mobile industry, but they were not making nearly as much profit as Intel was, because they were basically selling IP to lots of implementers. But they had enough big companies with the killer app mobile, focused on building that ecosystem up. And so, ARM had helped because of the killer app funding, I guess, a lot of the ARM ecosystem work. So here we are with RISC-V. I kind of alluded to our strategy, and it was talked about earlier. I mean, we're in a unique position to take advantage, since we're open, take advantage of all the university brain power that exists throughout the world. Extremely smart people and professors and researchers, and so we're definitely trying to recruit them to the job of building out helping us build out the job of the RISC-V ecosystem. We want them partnering with professionals as well. So it's not just kids that are doing this work. It's industry leaders like Dr. Bao at the Chinese Academy of Science, for example. So getting people developed. So I think we've already started that growth, or started tapping into that angle of helping do all the heavy lifting necessary to bring us up to speed. And I think as companies, trailing along right now is big companies making money off RISC-V, where RISC-V is existential to their survival. So we're not there yet, but as we get there, and I'm confident will, those big companies will also start pitching it a lot. And I think Intel definitely is going to be a big help in that dimension. But so kind of linking the questions together, it would help a lot to have a killer app for RISC-V. And I don't think anyone could predict what that is, but I can kind of describe some qualities of it. So, part of my talk today, first of all, was to plant in people's brain that you want to build equipment with RISC-V and lots of RISC-Vs. I think the vectors, ISA can be an element in stepping up to the plate when the killer app does arrive. ARM has a vector processor part of their ISA as well. So we're kind of, we're not coming from behind there so much. So I think, definitely hoping people realize the value and the of the RISC-V vector ISA, and we'd get everyone starting to use that. I really want those to become the kind of the transistor of the next level of compute, and then the innovation is using those transistors. So the killer app, to be a true killer app, the PC business was a massive app that got computing in a lot of households. People were buying computers. The mobile, I think by any measure, I've looked at some numbers, is 10 times bigger, 20 times bigger. If you look at all the profits that Apple's making, Verizon's making, all these people are just making massive amounts of money off the mobile app or out of mobile. And so to the point where almost every person in the world has one of these phones, and every person is paying a bill. So how do we beat that? So a killer app should be 10x bigger. The next killer app should somehow be 10x bigger than mobile. So it's going to be it's a challenge. Now I'm going to go really out on an edge, and got to get all these machines to start making their own money and buying the next generation of software themselves. So if you want to, I don't know if that's a dystopic thought or not, but
okay. You're making a very big projection.
Yeah.
Okay. We do, yeah. I think we do see it's probably the evolution ongoing.
Yeah.
So I'd like to also want to hear from the others. What do you share with Ted's projection? Anyone had thoughts about what takes RISC-V to succeed, and what will be the potential killer app?
This is Rob. I was going to say an important aspect. So an important aspect, of course, is building a software ecosystem around RISC-V, a robust software ecosystem. And I know this from what I saw at Oracle relative to Spark, is that having a robust software ecosystem, the libraries, compilers, eventually into the applications, is the key aspect of making any architecture successful. But I will say that the openness of RISC-V and the collaborative nature of its innovation is what's going to help guarantee its success. A company or a person can adopt the architecture and generate an implementation without worries of other ramifications or licensing ramifications, if you will, right? In fact, so I do chat with Mark Kevelstein monthly, as we do collaborate with RISC-V, obviously, or not obviously, but we do. And I asked him one time, I said, gee, Mark, do you know all the use cases of where RISC-V is instantiated, or I was just kind of curious, how it was always built as an ASIC, or is it built as a custom, semi-custom, just kind of want to understand the implementation. And he said, I really don't know. It's used in so many places, I don't know. He couldn't really quantify entirely that for me. So I just thought it was rather interesting, and also a testament to the widespread adoption of RISC-V. So.
All right. Hey, thank you, Rob and Ted, on the topic. I think finally, we take two questions from the audience. I think one is the technical question is pretty specific, and the other one is non-technical. So the technical question is that what are the issues with chip-to-chip communications in the multi-chip package? Anyone? What do you see as the issues for chip-to-chip communications?
Well, I think what, go ahead.
No,
Please.
go ahead, Rob.
No, I was just going to say, I think the aspect that with AIB and now the subsequent follow-on partnership, I can't recall the name, so folks help me please. But I think the fact that the protocol and the underlying electrical aspects of the interface has been defined. I think that goes a long way relative to addressing some of the concerns. I know that in the case of a number of design teams, defining that type of thing is a challenge. So having that being donated to the community, if you will, as an open source standard is a huge benefit.
Yeah, that AIB has gone through several generations, so it is proven and battle tested, and pretty impressive, solving problems of power, bandwidth, and latency. So I think that's the least of the problems in getting it to take off.
I would say at this stage, there are actually multiple technologies available to enable the chip-to-chip. In fact, one of the topics showed up here. I think at this point, the industry most needed is actually industry standardization of the interface, which is what's happening today. Once that one is there, I think the next stuff we're going to be built on top of that platform. It is going to be tremendous progress starting at this point, which is good to see. That said, I'm really talking about existing technology. There's plenty of space for R&D, for example, in optical interconnected space, which is also chip-to-chip technology. That space is not there yet.
Okay, all right. Hey, thank you. I think one last question from the audience is non-technical. This is for Rob, that you have seen 40 years experience. What are the common attributes you see that successful engineering leaders? I think after Rob, we could, many of us could speak to this too. We'll start with Rob.
So the question was, what are the attributes of a successful engineering leader?
That's right.
Oh, that's a good question. I wish I knew the answer to that. But anyway, I will. I'll say this. First off, I would say is remain humble, no matter where you are in your career, because failure is just around the corner and success is fleeting. I think that's the first aspect. The other thing is to always listen to your team, and your team may be of varying backgrounds, right? Both in terms of engineering education, right? But your team may also include people such as legal or human resources, right? Or procurement, right? I certainly learned that in my experience at Oracle, that I worked with a very broad team, and each individual of those teams had valuable perspectives. So I think being able to take that information in and reason it and then ask appropriate questions hopefully lead to the right decisions being made, both from an engineering and a business perspective.
Okay. Yeah, I think it's more anyone else want to add? What do you see that you have been in the industry long enough? What do you see as the attributes to the successful engineering leader? Anyone else to add?
Yeah, so related to being humble, you want smarter people working for you. So you don't want to be the smartest guy. You want the smartest people working for you. I think that's actually crucial. I mean that's how you can lead. Get smarter people around you.
Yeah. Okay.
And maybe one thing I'll add here is technology world is definitely very, very competitive. So make sure you find the stuff that you're passionate about and have fun with it.
Okay. Michael,
that's great advice. I mean, yeah. I mean, I've enjoyed my job, so that's like hugely important. You spend at least a third of your life doing it. So,
yeah. Michael, any thoughts on the topic?
Yeah, so well, anyway, so I just want to make some good conclusion here is that again I see that I mean the semiconductor industry definitely there's a lots of the opportunity here for the innovation, right? And I mean I really kind of enjoying the all the other speakers talk today. And hopefully that with those the collective wisdom, right? I think we can working together, right, to make the more innovation, right? And especially one thing, there's one aspect I forget to share to in my a presentation there is that a lot of people is asking how to address the global shortage of the semiconductor, right? And especially that nowadays that it's a big problem. I mean, other than increasing the capacity, right? I think how can we do that, right? And I'm facing this type of issue, right, on a daily basis, right? Not just from the customers that I'm talking on a daily basis, but also from the advantage of actually our internal supply, right? And specifically, what we're doing is that how can we actually, increase the, the equipment, utilization, including the production engineering efficiency, improving the yield, or increasing those, production, throughput, right? Those are the things that, it's a big question that the industry, are, struggling and, and have to deal with, right, on a daily basis, right? So what we see particular beneficial, right, to actually, with the, applying the AI and the machine learning, what we see in particular benefit is that using those, a lot of these advanced techniques, right? For example, we do this, adaptive testing, right? Or improving this inline, outlier detection, or doing this, a lot of this, guided kind of analytics kind of techniques, right? We are seeing that, not just for the customer, right, but also inside the Advantest, right? Because we are seeing that there's the big backlog, and customer are just keep pushing. How can I increase those throughput and efficiency? And what actually makes me feel that, has a sense of this kind of achievement, I think it's not just on the, on the business, actually, from the technology and also the manufacturing efficiency. I'm seeing that with those AI analytics, right, we were able actually being to see some significant improvement from those, throughput, right, from the manufacturing and the yield, right? And this is actually what actually makes me feel excited and keep me motivated. So
yeah. Hey, thank you, Michael, to share your personal chat. I think right now for the this is a great topic, and we have a great lineup of the speakers. It's very hard for me to let go. We could spend hours chatting, right? We can spend years working on the future technology trends. But sadly, we have to conclude our panel discussion today. There's only certain things. Our time is up, and I again greatly appreciate all of you to join our speakers remain and join the panel discussion. And I appreciate the CASPA Symposium team. It's a well organized event. At this point, I have to pass back to the William.
Hey, thank you, guys. So before we let you guys go back to join your family for dinner, we'd like to bring our chairperson of this event, Ian, for the final prize drawing. So Ian, go ahead.
Hello, everyone. Thank you. I'm Ian. I am the head of Symposiums for CASPA. Thank you very much. Thank you. Special thanks to our speakers who joined and brought great topics, great speeches and discussion to our audiences. So as appreciation to the speakers and audiences, we actually brought this prize draw as appreciation. So let me get the slide. Okay, so you're able to see my screen, right? Yeah, so here is the prize drawing code, but I guess we have a lot of registration already. What will happen is we need you to present to Ring and confirm yes in the chat room, and the e-gift card will be sent you through email. So we have two $25 Amazon gift card and one $50 Amazon card as the #1 prize. So let me start with the drawing now. We have 80 people, 82 people registered. So what will happen here is I will from number 2 to number 83, I will use a random generator to generate a number, and whoever got it will be the winner, lucky winner. So number 1, so first the first $25 Amazon card. Okay, number 57, right? Let me double check. Yeah, number 57, who is the lucky winner? Is Jason Lee. Is Jason Lee here?
Here's Jason.
Jason is in? Okay.
Yeah.
Okay, sure. So Jason Lee, let me $25, $25. Okay. So next one,